Hello, everyone. Welcome to this week's Crunch seminar. Today we have two speakers. Our first speaker is Zekun Shi, who's a second-year PhD student from a School of Computing at the National University of Singapore under the supervision of Professor Kenji Kawaguchi. He also works as a research engineer on the AI for Science team at CAI Lab. He works in the intersection of machine learning and physics, especially at initial electronic uh, structure modeling. Before his PhD, he obtained his bachelor's degree in mathematics from Nanyang Technological University in Singapore. Second, thank you so much for your time today. And with this short introduction, you can start whenever you're ready.
Thanks for the invitation. So here today I'm going to talk about our recent paper published at NeurIPS 2024, Stochastic Taylor Derivative Estimator. So today I'll go through the outline here. We'll first go through the problem background, and then we'll talk about the two techniques that I use in the paper. One is amortization, and the other one is Taylor mode AD. And then finally, I'll talk about some experimental results. Yes, so for the background, so we're interested in this kind of optimization problems. So here F is some kind of arbitrary function, U is a parameterized function class, usually it's a neural network, and D here is a differential operator. So naturally, this kind of loss function appears in a lot of settings. One of the most prominent example will be pings, which is the main focus in our paper. But there are other potential applications as well. So one of the main difficulties in computing this kind of loss is that typically, for example, in PDEs, the D operators here, they will typically contain at least a second order derivatives. And if we use neural networks, naturally, to compute high order derivatives, the simplest way is to just repeatedly apply the backward mode AD. So for example, if you want to have, if you want to compute these second derivatives in JAX, this is the simplest way that you can do. Or if you use PyTorch, yeah, so this is how you do second order derivative by repeatedly applying backward mode AD. But later on, we will show that this is actually quite expensive in both memory and compute when either the input dimension or the derivative order are high. So now let's dive in a little bit. So first of all, you never want to compute the entire derivative tensor because this has exponential scaling in K. So just for a quick illustration, so if you have a scalar value U, then the first derivative, the Jacobian, is a vector, and second derivative is a matrix, and the third derivative is like rank 3 tensor. So as you can see, this grows exponentially, and you will never want to store this explicitly. So actually, backward mode avoid storing this, but still it has exponential scaling. So let's see why. So let's consider like a 4-layer neural network where the hidden size are H and the input dimension is D. So this is the forward computation graph. So you start with the input X, and then after the first layer, you get intermediate output or activation Y1, and then you get Y2, Y3, and in the end, you get the output Y. So when you apply the first backward, this is what happened. You will create so-called this VJP graph, which is essentially has the same length as the forward graph, but running backwards. And the other thing is that it has this kind of dependency on the forward value or the activation. So for example, if you want to compute this V2 transpose node, you actually need the value of Y2. So you can only compute the backward mode once the forward mode is done, and you also need to store this activation trace Y1, Y2, Y3. So now if you do it a second time, So you basically treat the first row as your forward graph, and then you will create, as before, a backward graph which has the same length. And then you also need to store this V1, V2, V3 on the first row now. So as you can see, applying twice, you can see the pattern here. This has an exponentially growing number of sequential nodes, and also the number of activations you need to store also grows exponentially. So if you apply a third time, you will need to store the second row, and then this whole computation is also like twice as long. Yeah, so then we can do some quick asymptotic analysis. So in terms of memory and compute, you can see that there's a clearly like exponential scaling in K as well, even though we're not computing the derivative tensor explicitly. So yeah, so from here we can see that there are a curse of dimensionality. So here we have like a scaling in D, and there is like a exponential curse of in K due to the higher order derivatives. So how can we tackle these two curse of dimensionality and the curse of high order derivatives? So we're applying two techniques. One is amortization and the other one is Taylor mode AD. So let's first explain what is amortization. So the idea of amortization is that if you have an expensive operation and then you are doing some kind of iterative optimization, then at each step, you can actually replace the expensive operation with a cheap stochastic estimator. So the most well-known example of this is perhaps stochastic gradient descent. So instead of using the full batch, you can actually use a mini batch, and that's much faster, although it will introduce some kind of noise. But in the end, you still converge. So we can apply the same idea for derivative operators. So actually, so let's look at the case of Laplacian. So this is actually first proposed by my co-author Zekun back in a paper in 2023. So if you look at Laplacian, it's basically computing the diagonals of Hessian or the trace of Hessian. And if we view each element of the trace as a data, then we can kind of perform mini batch gradient descent. So if the trace is the full batch, then if you randomly sample, let's say B number of these elements, and then this will form a mini batch. So if you do that for each step, the cost will be much lower because you have replaced the scaling in D with a fixed scaling of B. So here B is the batch size, which can be a constant here. Yeah, so with these techniques, you can already solve very large PDEs. So you can perhaps solve like 100,000 dimensional PDE within 12 hours, which is very impressive already. But we will show that this result can be improved much further by using a more sophisticated AD technique. Yeah, so we want to amortize more efficiently. I mean, explicitly, we want to reduce the scaling in K because, as you can see, that although the scaling in input dimension D is reduced, this exponential scaling in K still persists because you're still doing repeatedly applying backward mode AD.
Can you remind us what is K? K is?
K is the order of the derivatives. So here for the Laplacian, it will be 2. Yes. And we also want a very general framework so that given any derivative operators, we can come up with the amortization scheme. So we will first do generalization. So we will revisit this classical technique called Hutchinson trace estimator. And here is a very short proof why it works. So basically the idea of Hutchinson estimator is that if you want to compute the trace of some matrix A, you can actually perform some kind of random projections with this vector VI. So you can draw a batch of VIs and do this VI AVI contraction, where VI is coming from a certain distribution. And in expectation, this will be equal to the trace of A. And the key property is that the distribution P should satisfy this property. It's basically like an isotropic property. And usually you can satisfy this with an isotropic Gaussian. And the minimum variance choice will be the Rademacher distribution. So the key observation here is that we can view this random projection. So if you look at the blue part, you'll be kind of like applying a mask to a matrix. So here, due to the isotropic property of distribution P, so this expectation is just equal to identity. And here in the basically the first line in the end says that applying this random projection with V is equivalent to doing a tensor dot product of A with the identity, and that extract the diagonals. So yeah, we can use this to generalize HTE for arbitrary linear derivative operators. So first step would be to write, so to kind of rewrite action of a linear derivative operator on a function of U as this kind of as kind of like applying a coefficient tensor to the full derivative tensor. So here, for example, so if L is the Laplacian again, and so the special case of 5 would be like in this equation 6. So the derivative tensor will be just the Hessian, and the coefficient tensor will be just the identity. And yeah, so this works for any linear derivative operators of any order. And suppose one can come out with a similar kind of random projections. So here, for higher order, we'll be doing kind of like repeated chronicle products. So analogously, this is like a higher order generalization of this isotropic property. So if we can find this equation, this kind of distribution P that satisfies equation 7, then we can rewrite the action of L on a function U as such, so which is the equation 8. So in the paper, I've shown that there is a way to find this P. So I'll not go into the detail here. But the main point is that now we get this expression 8, so we can rewrite the action of L on function U as expectation. And this expectation, then we can apply Monte Carlo integration, just as in the case of regular HTE to convert this to like a mini batch setting. But now the problem is, okay, so you have this expectation, but what's inside the expectation looks still complicated, because this is like you have a full derivative tensor, and then you are doing a tensor dot product with this chronicle product. So can this really be computed efficiently? So the answer is actually yes, but it's slightly convoluted. So to able to, we will come up with a way to compute this equation A, specifically what's inside the expectation, without actually compute the full derivative tensor dk of U. So in order to do that, we need to use Taylor mode AD. So let's recap a key concept, that is the directional derivative. So basically, directional derivative, we can think of it as like change along a line of a function. So here, let's say we have a scalar function u on a two-dimensional domain. So here, this blue surface is the graph of u. And let's say we have, we want to evaluate the directional derivative of u at point A along a direction v. So this is equivalent to restrict the function to this plane and then calculate like a scalar, just simple derivatives. And the connection to regular partial derivative is that if we fix the direction to standard basis, we'll be computing regular partial derivatives. So this is what I've explained. So if we want to compute, the derivative, directional derivative of u at point A along the direction of v can be think of u compose g, and then you take just the scalar derivatives. So here g is this curve that we have defined here. And in the last line, if you just apply the chain rule, you'll find that this is actually a Jacobian vector product. And this is the so-called forward mode AD. So instead of looking at the greatest descent, instead of computing the greatest descent direction, you're asking, what the function will change, the amount of change given a certain input direction. And yeah, so the compute graph is a bit different here because everything is forward. You don't have this backward dependency where you first need to compute the function value y and store everything and then start to go backwards. For forward mode, everything can be computed forwardly. That means once you compute y1, you can discard it because you compute y1, v1 together, and then you just keep going forward and you never store anything in this case. So this can be generalized to higher orders as such. So just now we've been thinking about directional derivative by thinking how the function change along a straight line. So in general, we can think of the rate of change of a function along a curve. So here, just now, this straight line has only first order derivatives, but in general, you can have like up to kth order derivative because it's a space curve. So here I'm representing it as v1 to vk. And also you can consider, not only the first order rate of change, but up to kth order rate of change. So this is like a higher, this is the generalized high order directional derivative operator. Here I write it as partial k. So what this reads is basically the kth order of rate of change of u at point A along this curve G, which has up to kth order derivatives. And the important thing is that this concept actually has a closed form formula, which is called the Fadi-Brunos formula. So it looks kind of complicated, but the important thing to notice is that this blue part, notice that this is exactly like the full derivative tensor, tensor dot, some kind of conical product of some vector. And that is exactly what we want, almost, because this is a summation of such terms, and we also have like this extra coefficient at the front. But in the paper, I showed that there's a way to basically come up with formulas to express arbitrary contraction as high order directional derivatives. So this is getting a bit abstract. So let's use some concrete case to illustrate what I just described. So one of the key results in the paper is that arbitrary contraction of the derivative tensor of kth order can be computed with nth order directional derivatives, where this order is at most k times k plus 1 divided by 2. So here I'm showing the result for a concrete example for order 2. So for order 2, we are considering the contraction to Hessians, and there are basically two possible contractions. You can either contract Hessian left and right with the same vector v, or with different vector v and v prime. So here I covered the two cases here in equation 12. So if you want to compute just this kind of bilinear form v Hessian, so v transpose Hessian then v. So this is the correct input for the high order directional derivatives. So you just set the primal to A, and first order input tangent to V, and the second order to 0. For this, for contraction with different input directions, then this is the correct one. So notice that here we need to go to a third order directional derivatives here. So if you're interested in like knowing how to compute arbitrary contraction like a closed form formulas, so this is actually not in the paper because it was out of scope, but I have put out some discussion on the GitHub page that we have for the code, and yeah. So also like how this is actually done in the code is that so JAX provide this so-called Taylor mode AD, which basically computes these high order directional derivatives following the Fadi-Bruno's formula. So notice that it actually does not use Fadi-Bruno's formula like vanilla-ny. So it doesn't follow this verbatim, but it actually derive closed form analytical formulas, so that so basically you can compute this from order 1 to order k directional derivatives altogether or recursively from order 1 to order k. And if we look at the compute graph, the scaling in k is linear because so for each derivative order, it's just like in forward mode, there's additional row of nodes, and they can either be computed all in parallels or sequentially using some recursion. But either way, the scaling in k is now linear instead of exponential. So here again, I'm showing the simple example of up to order 2, what this actually computes. And you can get some intuition on like so what it actually computes by looking at this last piece. So this is not just computing the part that we want, but it also contains this extra part. And this is why in equation 12, the last input here, it will be 0 because we want to remove this unnecessary part. Yeah, so finally, let's talk about some experimental results. So we did a lot of experiments with various kind of equations, and essentially we're just applying various techniques to a regular pin and see how fast we can achieve convergence and also the memory usage. So this is, I believe this is like one of the main table that we show in the paper, and this is Allen Kane equation with inseparable solutions. So here I'm trying to apply various different kind of techniques to show the gains of our method. So first, in the first row here I'm just showing the result from the previous paper SDGD with PyTorch implementation. And because our latest code is written in JAX, so I also re-implement SDGD using JAX. So this is the second row. And I've also done some enhancement to the base code. For example, previously in SDGD implementation, the mini batch is not parallelized. And so I've done that. So this is the third one. And the fourth one is
Hi, a second one question here. Like, so you say that the only difference between the first row and the second row is the framework, right? The second one is in JAX, the first one is in PyTorch, right?
yes.
And
Here
and,
only
and
the
in
first.
and in this table, lower the better, right?
Oh, sorry, higher the better, because this table is speed, like iteration per
Oh,
second.
okay. I see. Higher the better.
Yes.
So
because
so
they are
JAX
typically,
is like 10 to 20 times faster than PyTorch.
well, I mean, so the PyTorch implementation is not optimal as well, but here I'm just showing that the framework could make a difference. So I'm just trying to ascertain like the gains. Because if we
Okay.
just directly look at the last line, is not apparent where the gains are coming from.
Okay. And one question, and in terms of accuracy, you get the exact same accuracy, right?
Yes, so I didn't report the accuracy here, but if you look at the paper, I have reported the relative L2 errors. And they are essentially of the same order because in terms of model parameterization and the objectives, they are all the same. It's just that how we compute the loss at each iteration is different.
Oh, okay, I see. Thank you. And one question, so why do you run out of memory with JAX and you don't with PyTorch? So PyTorch handles it better somehow?
You mean between the first and second line, or?
Yeah, when you go to 100,000 dimension.
So here, it
Yeah, if
could
you go
be
to the fourth row, it says OM, right? It's out of memory.
fourth row.
Sorry, four column, second row.
Yeah. So this well, I haven't systematically investigated this, but one of the reason I can think of is that because I use a lot of VMAP in JAX, so this basically prioritize things, and when you do that, it tends to allocate more memories. Like there's an overhead for that. Yeah, it is
Okay.
faster, but it takes up more memory. And
Okay,
this
I
is kind
see.
of consistent with what we see here. So it's faster, but it takes more memory.
Okay, got it. Thank you.
So Shi, there's just one question on this table. So if you're using batch, so why it is going for out of memory?
Sorry.
If you are using batches, then why there is a out of memory? If why this out of memory is happening? If you are using batches, right?
Yes. So like even for actually all these techniques besides the forward Laplacian, they are all like applying amortization, which means they use mini batch instead of like full batch. But as I said, you still need to store the activation, for repeated backward mode, and that is taking up a lot of memory once you scale up in terms of dimensionality.
Yeah, but if you're reducing the batch size, if you reduce the batch size, then that storage will be catered for. That if
I mean,
you can reduce the batch size, right? Just to store the activation. So, but if you're going for higher dimension, you can reduce the batch size. So the out of memory shouldn't happen if you're using batch. So,
well, yes, but they will still scale with the input dimension.
How small of a batch can you take?
Well, the minimum batch size would be 1. So this is the lowest that you can take. So here, okay, so I forgot to mention here in this table, everything is with 100 batch size. Obviously, if you reduce it to a batch size of 1, you can get a better performance in terms of memory.
But you will
But
lose
still,
accuracy. You will lose accuracy, right? That's what I'm saying.
Actually, surprisingly, for this particular set of equations, the convergence isn't really, I mean, it actually converges still pretty well for a batch size of 1. So I did some additional experiments as well, comparing different batch sizes. And actually, during the conference, when I talk to people, they also say that for some other application, they also observe this phenomenon where the batch size of 1 is actually enough. But I wouldn't say that this observation is valid for all different kinds of different optimization problems.
The question, when you say batch size of 1, you mean that you're only using one sample to do the...
Yes, yes. So it's like when you compute the loss that contains, for example, the Laplacian, you only take one random diagonal elements.
But ideally, I don't remember that much well, but I thought that, for example, a batch size had to be like an unbiased estimator of the full domain.
Well, yeah,
So,
it is still unbiased.
and
So
it should be representative too, right? Because what if you, I mean,
okay, so I guess
what
that
if you
there are,
have some part of the data who would want to go to the left and another part who wants to go to the right? And if you train it with one batch at the time, your optimizer will be stuck in the same place, right? Because in one step you take the left, and in the next step you take the right, so you will not move to any
yeah,
points, right?
that could happen. Like actually, in a previous paper, we did some analysis on like the source of variance. So you can do some variance analysis a priori, and you can actually construct like very pathological cases where, you know, applying so some you know, doing mini batch on the diagonals will give you a pretty poor result. But for that, you can actually use a different strategy for sampling. So like, because here, as I mentioned, so here we want, so for example, for the case of, let's just think about the simple case of HTE. So we want a distribution P that satisfy these isotropic properties. So there are many different ways to do it. So for example, just now I described that you can use a Rademacher distribution for P. And in SDGD, what actually happens is that this VI, sorry, this V is actually always like standard basis vector. So this is an entirely different distribution. So like instead of sampling from let's say Gaussian, you're sampling let's say a standard unit vector in x axis and y axis and z axis, so on and so forth. And they have different sorts of variance, and you can actually create a very pathological cases where if you do it with standard basis like in SGGG, it performs very badly. But in that case, using like Rademacher would be pretty good. So
Okay.
I guess it would depends on the problem, but for all the cases we consider here, we just use like this sparse version where you apply standard basis, and that's enough.
Okay, great. Thank you, Sekun.
Sorry, Zekun. I also have a question. This is Kyle.
Yes.
So I was also wondering about the accuracy question, and I wonder maybe for example, if I have a problem like the solution U its derivative with respect to h1 is very small, 0.1, and with respect to h2 is like very huge. Then if you just sample the h1 to the index one to be the sample in the STDE, then is it going to be not very accurate because it doesn't really reflect the derivative to other indices.
So I was saying, so sorry, can you repeat? Like you say one.
Right. So I was just yeah, I think I basically had the same question. So Huang mentioned like the question whether sampling one index is representative enough to all of the indices. So I was just curious to like have you tried some problems that the derivatives are not very uniform across all the indices. So like if you sample one subset, one batch of the indices, it might not represent the entire the entirety of the data points.
Okay, so answer your question, we haven't done that explicitly in this paper. And also we're not doing like a uniform sampling if that's the case. So for example, you can actually do like a weighted sampling. So if you think a priori, you can do some analysis. If you think certain, so let's say you have a 5x5 matrix and you think the third position on the diagonal is actually more important, then you can assign some weight. So you can do something like importance sampling. Yeah, but to answer your question directly,
Yeah.
we haven't
Yeah.
done that explicitly in this paper.
Right.
but
Yeah.
yeah,
I think that helps. Right. Right. Yes. Thank you.
Okay, so another thing I want to point out in this table is that so I also compare with this technique called forward Laplacian. So because in this specific experiment, the derivative operator in question is actually a Laplacian. And this is like a very specialized AD rules developed for Laplacian. And it performs really well, but because it does not do amortization, the scaling in D is actually quite poor. So it performs really well in low dimensional cases, but once you scale up the dimensionality, the performance drops drastically. Yeah, so here is the table with the actual memory count. So you can see that even from 1 million dimension, our method only use like 6 gig of memory. So yeah, we can still push it higher. So I think in the end, we managed to do 5 million dimension on a single A100 GPU. Yeah, then here it's also open source, our code. So you can just type in STDE search in GitHub. You should be able to find our code. And yeah. And just to give you some like frame of reference, just now we mentioned that with SDGD, we can train 100K dimensional PDs in 12 hours. But with this kind of speed, we're doing 1 million dimensional PDE within 10 minutes. Okay, so yeah, so that's all for the code. And if you have any further questions, please let me know.
That was a really great talk. Thank you so much, Sekun. Do you have any questions from the audience?
Hi, can you hear me?
Yeah, can hear you.
Yeah, I have a question. So, speaking of accuracy, I have like a similar question. And also at the last, you mentioned that the framework can be used to train pins for like even 100 or even like million dimensional PDs. I wonder with this like stochastic Taylor approximation, also the amortization you mentioned earlier, can you still get an accurate prediction of PDE solutions with your stochastic Taylor derivative estimator?
Yeah, so this is actually, I guess there are like two aspects in terms of this question. So the amortization technique is already proposed in a previous work in SDGD, and I think the accuracy of the results is already verified in this work. But basically what I'm saying is that if you apply amortization for a lot of pings problem, you'll still get an accurate solution. But I would not say that we're trying to get like machine precision here. That's like, we're not trying to do that. I believe it can be done, but it's not the main focus point here. The main focus point is like, we can do amortization much better by applying high order AD techniques. And if you have any method to boost accuracy, they can still be incorporated. So for example, let's say you do gradient enhancement, it can still be incorporated.
Mm-hmm. Got you. And have you ever done any experiments? Because I think my question is that you're definitely trading off some accuracy by doing the approximation, but you're saving the computation and also memory by a lot. I just want to understand what is the trade-off, like say how much accuracy do you sacrifice by doing this approximation, like and also it is, if I want to solve PDs in practice, like how reliable is that for I to use the stochastic Taylor derivative estimator?
Okay, again, to answer your question, so in this work, I will say the accuracy that we get is essentially the same as SDGD. So any conclusion drawn from that paper, like in terms of accuracy, is still valid. It's just that the speed and memory usage can be lower by a lot by using this alternative way to compute the gradients.
Okay, got you. Thank you. Very interesting work. Thanks.
I see. This is Raj from Brown. First of all, very nice work. I just had a couple of questions. If you can go back to slide 17.
17, okay.
Yeah. 18, sorry.
Okay.
So here, the first equation, why your dual is 0 here? Like V is a primal, right?
Yes. Sorry, so A is primal. And here I write partial 2 because this is already a second order directional derivatives. So, so just as I explained, geometrically, this means that we are looking at the rate of change of U along a curve. And this is actually a second order curve. It's not a straight line. You can have, a second order derivatives. But for our purpose, we want to set this to 0. Because if you look at, actually, I have written out the exact analytical expression for second order directional derivatives here. So here, this V2 is the second direction or the second order change of that curve. And V1 is, V1. And we also, and we only want this second term. So that's why we are setting V2 to 0 in this case. But it could be that like you're doing some application where you actually have exactly an operator of this form, then in that case, you can actually set V1 and V2 to the correct value.
So in that way, your derivative estimation is biased because it depends on V, right? Here, so it is a VI, VJ. So this estimation is biased, right? Because it depends how you sampled VI and VJ, or how do you choose VI and VJ?
Okay, so basically this goes back to here. Basically this is equation 7. So because we can find a distribution P of this V, these all different V's, and this equation 7 is basically saying we are trying to find P that is unbiased. Because in the end,
and what are those distribution, like any distribution, like with non-zero higher order moments or any low order
yeah,
moments?
So in the paper, we describe two different ways to construct P. For some special operators, you can use, for example, in the case of HTE, you can use isotropic Gaussians, and also for biharmonic operator, there is also like you can use isotropic Gaussian as well. For a very general case, it is as what I described. You will use like a sparse construction where all these VI are actually standard univectors. So yeah,
Okay.
that's the most general construction.
Yeah, if you're choosing the isotropic Gaussian, then it is a non-biased, that is for sure, because we did similar line of work and where we estimated the gradient with the forward mode, but direction was chosen from specific distribution with higher order moments. So, yeah, and this is a good piece of work. Really appreciate. Really, thank you.
Can you? I have a question on what happens. Do you get any gains if you have only 3 dimensions?
Okay, so yes, so this question is very good because I didn't show it in this graph, I mean these two tables, but we also did low dimension but high order equations. So in that case, yes, you will still get a gain. So the gain, because the scaling has two parts. One is with the input dimension, the other is with the order of derivatives. So if you have like a low dimensional case, but also low order, like order 2, then the gain is not significant. But if you have like slightly higher order, but still like low dimensional case, for example, perhaps like 2-dimensional but like order 5 equation, then yes, you can still get some gains. But in that case, we will not be applying amortization anymore because the dimension is so low. We'll be mainly just focusing on how to actually compute those derivatives with the Taylor mode AD. So yeah,
and the fatty Bruto formula, you use that there, right, for the high order derivative.
yes. So the main thing for that kind of application is to come out with expression like equation 12. So basically, you want to express some kind of partial as some linear combination of high order directional derivatives. The point is that because this partial n on the left can be computed quite efficiently.
Yeah. Thank you. Yeah, because I remember with JU, and we have to go to high dimensions to see in SDGD to see a gain. So
yes. So this is also like a very common question, and people will ask. So in what kind of real application will you be encountering this kind of case? So for me, because I have been working on basically quantum chemistry simulation for a while. So one of the prominent case will be quantum many-body problems, because in those problems you'll be naturally 3n dimensional, where n is the number of electrons. Yeah, but other than that, I guess another natural occurring example would be low dimensional but high order. I believe there's a lot of such equations in fluid dynamics.
Yeah. Thanks, Zekun. Do we have any other questions?
it goes up to 4th order, but not higher. in fluid dynamics, 4th order is the highest that I know. Can have a biharmonic.
Oh, also like I've record that people mentioning like you can do stability analysis with Taylor derivative. So that's another application. Yeah, but I mean in this paper we're only focusing on solving PDEs.
Yeah. I mean, Fokker-Planck equations are usually very high dimension.
Oh yes, that is another thing that we are actively looking at. So
And the
potentially,
Hamilton-Jacobi-Bellman equations that we did with Zheng Yun, because they used in controls and could be arbitrarily high dimensions. It's a parameter space, so.
yes.
Do you have any other questions?
Did you mention that, Juan, did you mention that this paper was they received the #1 NeurIPS award?
Oh, I think I didn't mention it in the but it was in the information that I sent them in the email. It was
Okay.
yeah. But it was a really, really nice work, Zekun.
Thank you.
Maybe one question, since if nobody else has another question, like, did you try to analyze how this time scales with the size of the network? Like, if you use like bigger networks, how slower will it become, or when it's like?
Okay, I see. So yeah, I haven't really done like real experiments, but if we go back, okay. So from here you can see that definitely everything scales with the network. So here L, so here I'm just using like a simple V4 networks. So L is the number of layers and H is the hidden dimension. So it definitely scale with the network size. But yeah, we haven't done any experiments in terms of like just testing out how it scale with the network size. So all these experiments is done like with fixed network architecture. Sorry, Juan, you're on mute.
Oh, sorry about that. And could you please remind us what was the architecture? How many layers and layers you were using?
Oh, okay. So for this case, I believe is 4 layers and hidden size would be 124.
Okay,
But,
that's
yeah.
considerable. That's quite good. Okay. Thank you, Sekun. Do we have any other questions from the audience? If not, I think that Suku is here. Suku, are you ready?
Yeah,
Are you
yeah,
still here?
yeah.
Okay, great. In that case, Sekun, thank you so much for your time today. I know that was a bit later, so we're all grateful for
No
your
problem.
time. And once again, congratulations for your award. You is well deserved. You did a really great job.
Thank you. And thank you everyone for attending this talk. So stop sharing.
Can I share my screen?
Yes, can you please try sharing your screen?
Suku, welcome back.
Oh, thanks.
It's like you never left.
Oh, I feel I've left, right? Yeah. Okay, I think it's. Can you see it now?
Yeah, we can see. Can you put in presentation mode, please?
It is in presentation. Let's see. Oops. Shift. Gosh, I don't know how it didn't go. Wait, let me start it before again. Now?
Yeah, now it's good.
Good,
Great.
okay.
Okay, thank you, Sugu. Okay, and we have our second speaker today is Professor Sukumar, who holds a PhD in theoretical and applied mechanics from Northwestern University. He was a postdoc at Northwestern University and a research associate at Princeton University before joining UC Davis in 2001, where he's currently a professor in civil and environmental engineering. Sukumar is a regional editor of International Journal of Fracture and a member of the editorial boards of Computer Methods in Applied Mechanics and Engineering and Finite Elements in Analysis and Design. Sukumar current research focuses on maximum entropy and deep learning-based PDE solvers and developing virtual element methods for the formation and fracture of solid continua. Suku, with this short introduction, welcome back, and it's always nice to have you here. And whenever you're ready, you can start.
Sure. Thanks a lot, Tuan, and thanks for the introduction too. So it's good to be back, at least virtually, today. And many of you, of course, I've met in person, and those of you, of course, hello again. So anyway, this work is joint with Amit Acharya at CMU, and as the title says, it's more to talk on PDEs rather than pins or ML. But of course, as I'll show you, it can be applied to many different approximation methods. So it's more a framework or a different approach to solving a PDE is what I think of it, right? And in fact, let's hope this link works. Okay, so this is a paper in case you want to take a look at it. And my talk is largely based on this paper, but only parts of it, the paper, since I won't be able to cover all of it in one shot, of course, given the amount of material in that paper. Okay, so I thought I'd provide some background and motivation on what are primal variational formulations first, before delving into this dual variational formulation I'm talking about. And just to remind you that you can stop me anytime, since I don't want to put too much information, because it's rather a lot of math is coming up, essentially, all of it, right? And before going there, in fact, I thought, I put this link below. It's a very, very nice, beautiful video, which I found a few months ago on showing the action principle, basically in action, so to speak. And I could not put the link here, so I'll just see if I can click it. And it's a 20-minute segment. I'll show you just to give you an idea, because I think it's good to view this video before my talk in some sense, especially if you're not familiar with the connection of ODEs and PDEs and to their this is a strong form compared to the variational perspective, how you can minimize to take the action of something and then minimize basically that, or the least action principle. So let me see if this goes. Yeah, so this is I'll just show you 20 seconds of this, and then now you have the link and you can go back and view it. It's half an hour, this video. So I'll just play.
This is a video about a single simple rule that underpins all of physics. Every principle from classical mechanics to electromagnetism, from quantum theory to general relativity, right down to the ultimate constituents of matter, the fundamental particles. All of it can be replaced by this single rule. Feels like we're approaching spooky territory. We're approaching.
So I'll stop there, and some of you might know Strogatz from Cornell, who was the last, who was talking at the end. So the idea is that basically, instead of viewing PDEs from the strong form or the equation point of view, it's more, you want to see a unifying principle, and that's what is the action, or the principle of least action. And then you can view the video for more insights on the connections of that to Euler-Lagrange equations and so on, right? So anyway, so I'll present, now I'll go into the primal variational formulation, which is talked about in the video itself. And then I'll go on to the dual variational principle, giving you like a big overview picture of the whole idea. And then I think it's beneficial to look at it first from things we already know about, linear equations, nonlinear equations, and I'll take a quadratic equation, and my own work 20 years ago on entropy maximization, just to show you some of the ideas that can be linked to this notion of dual variational principles. Then I thought I'll pick just two problems and go over it slowly. And one is an initial value problem, so it's time dependent. And the second problem is a steady state diffusion equation, which is spatially, it's a boundary value problem. So then based on these two, you can then surmise, or at least infer, how one might tackle within this framework problems that are, for example, time-dependent convection diffusion or time-dependent heat equation, or many other problems, linear, nonlinear, and so on and so forth, right? So that's the background, so to speak. And I'll pause after at least a few parts I cover. First, I'll cover the background and motivation. I can pause after that in case you have any questions. Of course, you can stop me anytime if something is unclear. So let's start with background and motivation. And I want to first go over what are primal variational principles or variational problems. And I always like to start with one dimension because it's simple to understand and also it's familiar to most of you. So I take a one-dimensional elastic bar shown here, which is fixed at the left end. It has a modulus of E, the cross-sectional area is A, and the body force is B. So it has units of force per unit length. And the traction on the right end is sigma naught. And here's the equation. So EA U prime double prime. So there's a 2 primes on U, it'll turn out, plus B is 0. And on the left-hand side, you have a Dirichlet boundary condition or an essential boundary condition. And on the right-hand side, you have a traction boundary condition. It's saying that, okay, the stress is equal to E times the strain, essentially, U prime. So you can think of this as a Poisson equation, essentially. You just take E and A or heat conduction, for example. So you can represent many one-dimensional boundary value problems with this, right? So this is a strong form. And what one does in the weak form is to multiply this by a test function, do integration by parts, and basically realize that the test function should vanish wherever you prescribe essential boundary conditions. So it's stated in this form where UA is a bilinear form and L is a linear form. So AUW is equal to LW, and this is A, and this is L shown here. So you notice that the natural boundary conditions are incorporated into the weak form or the principle of virtual work, it's called in mechanics. And so you have to define spaces which must exist and from which you can only pick functions. So the trial function must be at least continuous and it must be 0 at 0. So you can only pick trial functions that are which satisfy this condition. And in this case, the test function also lies in the same space. But what happens is that if this trial function has a different value at 0, the test function still is 0 because you can think of W as a variation on U. So if U is fixed, then its variation at that point must be 0. So the nice thing about this, as well as many linear problems, and including nonlinear elasticity, is that exists this connection of, there's an action in some sense. There's an action which exists, which is in this case called the potential energy functional. In general, for dynamics, the action is the Lagrangian, formed from the Lagrangian, which is the kinetic energy minus the potential energy. Here, since the problem is statics, we have just this potential energy term here, which says half of AVV minus LV for V belonging to S. So the problem is that this strong form is solved by minimizing this functional pi of V, which states that among all V that lies in S, the solution U that solves the strong form is the minimizer. So that's basically the notion of going from function minimization to functional minimization or extrema or stationary points of a functional. So what one does then is so this is this whole weak form, this slide here, the middle part is what is based, is essentially finite elements are really based on this. Either the weak form or the variational form is used to implement all the methods, whether you look at linear problems or nonlinear problems. And the weak form is more general than a variational form here shown because you can apply to linear problems as well as nonlinear problems. And now just to give you a sketch of how one goes about implementing it, you choose a trial function UH in a finite dimensional space here, which is a linear combination of what are called basis functions, phi j, and uj are the unknowns. And you test it with, because you have, say, n unknowns here, you would like to test with n functions. So here you choose the phi j's as basically test functions also, because you choose them so that they are 0 at the essential boundary. Therefore, you can see that this must lie in S. So therefore, all the phi j's I choose are 0 here, essentially. So therefore, they also serve as suitable test functions. And therefore, by construction, your system will be, you'll be positive definite and all that, and you can therefore invert it, and you can solve for this KD equal to F system, right? And these are the constructions of what is called a stiffness matrix in finite element terminology, and the force vector acting. It stems from essentially this. So in a nutshell, this is one dimension, but it's very beneficial since essentially the same principles and ideas extend to multi-dimensions, but now you have to use a bit more of vector calculus. Other than that, it's essentially the same idea. So I just put together a couple of extra slides. First, starting with, okay, now if I have steady state heat conduction, you have basically a conductivity here, tensor here, kappa in general. And if it's a scalar, it's just an isotropic heat conduction. And I'm assuming, say, Dirichlet boundary conditions on the entire boundary. So this is my strong form. And associated with that is, again, the same terminology A and L. But now instead of the derivatives, you have gradients dotted with each other, right? Gradient of U dotted with gradient of W. And since your boundary has fully essential boundary conditions, On the right-hand side, you have only the force contribution coming from F, essentially. And now you must look at spaces which are in H1, so which is C0 still, but of course it's slightly different in multi-dimensions. And again, you look for trial functions. Now, since the trial function is G on the boundary, which must be met, you look for test functions that are 0, essentially, on the boundary, which are suitable test functions. Again, you can see that the minimization problem or the variational formulation is identical. So you have the variational principle now, right? If I minimize this and I pick any function V, right, which is admissible, then the exact solution is the minimizer of this. But of course, I can pick any guess solution. And that's what you do with FEM. You keep refining it and you get better and better solutions because how you have this direct connection between the variational formulation and what you're solving for. And that is the purpose of this video, which is saying, okay, if you minimize this guy, then you're really solving that, is the Euler-Lagrange equations. And you can see here, I've just repeated the slide from before. I just added a G here now. And again, the phi J's are 0 on the boundary. So by construction, it'll be equal to G on the boundary. And again, I use the test functions because these are all 0 on the boundary. I get now the stiffness matrix and the force vector to basically be of the same form, but now in a high dimension. Okay, just to give you an idea of what is done in FEM, just one slide. So these are Lagrange finite element like basis functions, just to give you an idea of what are basis functions. That's because that's what is really adopted in some sense when you do neural networks. So this is general, the hat functions, if you're familiar with what are called hat functions. These are how they look like, but though when you compute them, you do it element-wise, which are called shape functions in finite element books and papers. So here I'm just showing you 4 of them, and with no boundary conditions imposed. But if I want to have 0 boundary conditions, say at the ends, so a simple way to do is knock off the last 2 guys, and I have only 2 unknowns. Essentially, the U2 and U3 are unknowns, and U1 is 0 and U4 is 0, and that's how you go about solving a boundary value problem with FEM. And now you can see that these phi2 and phi3 are valid test functions because they are 0 on the boundary. And that's to be kept in mind. You can also do periodic boundary conditions where you can wrap around the basis functions by changing the connectivity, basically, essentially, on the end. Or you can also do block boundary conditions, which we have done in quantum mechanics, for example, where there's a phase shift between the left and the right. And so that's what is done in 1 dimension. And you can extend this to 2 dimensions in multiple ways. One, the simplest way is to do tensor product constructions like this. I'm showing you in a 2-dimensional setting how these functions look like for a higher order. I think this might be a cubic function shown here. So what's good about this is that it's polynomial. So you can systematically improve it. You can refine it, or you can increase the polynomial order. So P refinement or H refinement. You can have different boundary conditions. I've just shown you sort of Dirichlet and Neumann. You can also Robin boundary conditions or mixed boundary conditions. You can have different resolution in space. You can have a lot of elements in one area compared to the others. So you can get that. It leads to very nice sparse matrices. So you can parallelize it. So that's really the benefit of all this, right? What are the downsides? One downside might be, okay, it's only C0. But for some problems which are very smooth, you might want to get higher order continuity, for instance, right? And just to segue to that is, in fact, what was mentioned coincidentally just in the previous lectures of the biharmonic. And in fact, I have this biharmonic right here. So now what happens if you have a biharmonic equation, like plate bending, for example? So you have the square. So this is the Laplacian to the square, you can think of it, is equal to F in some domain in 2 dimensions. And you have both, say, U and the normal derivative which is prescribed. So this is like a clamped plate in mechanics, the physical problem would be. The nice thing is that you can exactly do the same thing as before. You multiply by test function W, but then you have to do the divergence theorem twice to shift 2 of the derivatives from U to W. So you end up with a Laplacian of U and a Laplacian of W here. And you have essentially on the right-hand side the same F times W. So now these become the essential boundary conditions as part of the definition of the space. So now you can see that the test function and the trial function space must now be in H2, which is highlighted. And they both must be 0. The U and del U by del N must be 0 on del N. So it's essential that this must be the starting point, because if you don't have these conditions imposed a priori in your approximation for V here, then you're not solving the clamped plate problem. It might be a simply supported plate problem, so it's an entirely different problem. So therefore, that's important. And here, recognize that this is H2. So loosely speaking, you can think of, okay, if you have functions that are C1, which are continuously differentiable, then you're in good shape. So they are going to be in H2. But of course, it's much more difficult to construct finite elements. For example, you can use Hermite finite elements to construct C1 approximations. But that's the general idea. And now again, you have a variational formulation, which is identical to what I showed you in the previous 2 slides, the same form, half of AVV minus LV. But now the definitions of A and L have changed, but the ideas remain the same, that you pick your function from this space. So you pick any function which is H2 and whose value and derivative, normal derivative is 0 on the boundary. So among all those functions, the one that solves the boundary value problem has the least value of pi. That's the least action. The least action principle is again in play. And now I just repeated the previous slide again. Again, you choose the same approximations, test functions, and now you compute k and f, and that's how you proceed. But of course, now the shape functions have to be C1 continuous and not C0 continuous. So that is my sort of short introduction to sort of primal variational problems. And so before I start the dual part, so are there any questions? Or I can just continue?
Yeah, then you can just
Okay, sure. Okay, so now let's get to the meat of the talk, at least the starting point of the talk. What is the motivation of this? Especially if this is Amit's work initially, all the theoretical work is done. He's done before. Is that you can think of, okay, there are many classes of PDEs which are well known, of course, which do not have a primal sort of variational structure. And the simplest of them would be just convection diffusion, steady state convection diffusion, which I'm going to talk about in detail afterwards. And of course, it's a precursor to Navier-Stokes and other equations which are convection dominated in fluid mechanics, including sort of Burger's equation and other things, and transport problems. And also more in solids also, it's very interesting because there are a lot of problems with, for example, you have inelastic deformation and fracture of solids, you have buckling and instability phenomena, right, which are also very interesting. And if you go to the time domain regime, then you have time-dependent problems, both parabolic and hyperbolic problems, and a host of other equations, linear, nonlinear, which can be classified, which do not have a standard or a primal structure in an exact form, so to speak. So therefore, you can think of, okay, in general, if you're looking for solving PDEs, especially for such problems which are listed above, then it'll be nice to have a variational principle, because then it provides you a more robust way to get to the exact solution or get convergence in some sense, and therefore it opens the door to possibly using even FEM and other mesh-free methods, B-splines which are smooth, and also the sort of topic of neural network is, of course, well known to people here. So also neural network, because with neural network, it's rather simple and trivial to construct smooth approximations. So that's one of the things I will talk about later on. So what is the basic idea? So there's a host of references here, but I don't want to get too bogged down, but just give you the sort of the big view picture. So the idea is to devise a variational principle by treating the primal PDE as a constraint, and all this will become clearer once I talk about it with an example, as a constraint, and then you minimize an auxiliary convex potential. So all this will make sense subsequently. So what does this give you, right? This buys you is that it leads to a maximization of a concave dual functional subject to Dirichlet boundary conditions on dual variables. And there's an intimate connection, for example, with the work of Brennier before in these papers, on sort of, he shows sort of this hidden convexity, or for example, he was looking at the Euler equations and show that you can actually construct like a variational formulation for that. So there are some connections to that, and they are more elaborated in Amit's papers also to a greater extent. Okay, then what does this buy you? At least for those of you who are well familiar with pins, for example, you've been solving many nonlinear PDEs like Alan Kahn or Burgers, as well as very interesting sort of chaotic dynamical systems like Lorentz. And often they're solved with collocation pins, or also with cans, which have come around now, or any other network that you can think of, any other architecture, for example. But I think that probably using duality principles can potentially deliver more robust solutions. Of course, the caveat is always that there's a training to be done, right? But given that, if one can make improvements there, then it might open doors to at least recognize what are better solutions and how to modify the formulations, for example, right? That's at least my perspective for now, right? Okay, so let's start with the dual variational principle. So here's our couple of slides, just tell you the big picture with the main steps. And then I'll start with a ODE, with a set of algebraic equations, and then go on to other ODEs and PDEs. Okay, so let's first think of a linear equation, system of linear equations or nonlinear equations, ODEs or PDEs. So I'll think of G as a function of capital U. So you can think of capital U as my primal variables, and which lives in Rn, I should point out here, Rn. And so G is a system of, say, M equations. So you have M equations in N unknowns is the starting point, and I want to solve it. So now I show this formalism focusing on nonlinear equations primarily, right? So we'll do PDEs and ODEs afterwards. So what we do is we convert this to an optimization problem that is preferably convex by considering the objective function u. So we basically pick an objective function, right? That maps u to h of u. So h of u is something that I will select or you will select if you're solving a problem. And we'll choose, the choice is flexible and I want it to be convex, auxiliary potential. And in fact, I can tailor it to the nonlinearities in the problem. If I know something about the problem, I can basically tailor it to that depending on the nature of the problem and what to expect, so to speak. So that's at least the macroscopic viewpoint is this. Okay, now how do you go about doing this, right? So now what is the point? Is the step is that you optimize h. You have chosen h, subject to the constraints g of u is equal to 0. So you think of the equations, whatever is prescribed here, either it could be linear equations, nonlinear equations, or PDEs, or anything else, as the constraint. And associated with that constraint are what are called Lagrange multipliers, which also will live in Rm because G is in Rm. So you have M equations, so M Lagrange multipliers. And therefore, you can write the Lagrangian, what is called the Lagrangian, and the associated stationary conditions as the following. So L of h, because it depends on h, is h plus lambda dotted with g of u. So this is a standard approach for solving Lagrange multipliers. So constraint minimization is essentially solved like this. So you form this, and then you say, okay, what are my stationary conditions? The stationary condition first is that this must be, the gradient of this with respect to u must be 0. So that's gradient of h plus lambda dotted with gradient of g should be 0. And of course, you should also recover the constraint, right? So gradient of lambda with respect to lambda of L of h should be equal to g of u should be equal to 0, right? So that this recovers that, okay, it makes sense that this must be satisfied also. So you have now two conditions that must be satisfied, this condition and this condition. So now you can think of this as a mixed variational principle, right, or formulation. But now we're going to do something to it. So just to identify and make things clear, so we have the primal variables that live in Rn and the dual variables that live in Rm. So n and m need not be the same, of course. And we seek a critical point that solves u, and I'll call it u star and lambda star, that solves infimum of the u of LH, this sort of mixed variational statement, and sup of the lambdas, right? So that's the starting point. But notice that one thing is that L of h as a function of just lambda is affine in the dual variables. So this is a function that is convex and concave. If you fixed u, then it's basically convex and concave. It's the only function that is both convex and concave. So it's basically a minimizer. So you pick all the u's, and among it, you are going to pick the maximizer of the lambda, right? So then what is the crucial step we do is that you select the arbitrary convex potential H so that it permits you to define this map from the dual to the primal. So essentially you can write down U as a function of lambda. That's the key step that we would like to do and which we are going to do. And how do you pick this? We want it to solve the stationary condition, gradient of U, LH of 0. So from this condition, I want to create this map from essentially lambda to U. So that is the step I'm going to perform. So what does that do then? It says, okay, then once suppose I create this map, then I can basically say, okay, S of lambda is the infimum of LH of U comma lambda. And I know that this dual function is going to be a maximizer by construction, always a maximization problem. Or if you take as negative, it'll be a minimization problem, even if G is nonlinear. And to see that, you can just say, okay, what is del S by del lambda at the critical point is equal to, right? So if I go back to, I'll just go back to the previous slide, but I'll just show it to you now itself, right? So the result is that del LH by del lambda at the critical point turns out to be just G of the map, which I have just constructed, UH is equal to 0. And just to see that again, I'll just go back to you and then it'll be apparent, I hope. Right. So now if I say, okay, if I take del LH by del lambda here, so you have to apply the chain rule here, but one of the conditions is precisely this. But this guy is going to be 0 at the critical point. So essentially the derivative of the chain rule applied out here will be 0. So the only thing that remains is basically del LH by del lambda, which is this. And of course, that is just G at the map at the critical point, which is UH. So that's how you basically you eliminate essentially, because of using this condition, we get what we desire, in fact, right? So that's what happens in this approach. So that's how you can basically make sure that this is the the precise definition, and this is the problem you're solving. So we are solving by using this mapping. We are essentially solving g of UH is equal to 0 by doing so. So we exactly recover the, so to speak, in the language of variational problems, you recover the Euler-Lagrange equations for this problem. So if g was equal to 0 was the Euler-Lagrange equations, by using this conversion, like this map change of variables or change of fields, you can think of, we recover essentially g of UH is equal to 0. Okay, so of course, if n is very large compared to m, the dual problem only has m unknowns because it's in the Lagrange multiplier space. So therefore, it's beneficial, right? So suppose n is 1,000 and m is just 2, you have only 2 equations, then of course, you get basically only 2 unknowns there, right, which you have to solve for. So let's take a system of equations because it will help to clarify and also make sure whether these steps make sense, right? Okay, so let's take A as a matrix of m by n. So m equations and n unknowns, and x is the vector you want to solve. So you want to solve ax equal to b. And if n is greater than m, the system is underdetermined. You have more unknowns than equations, so there are infinite solutions possibly. And if n is less than m, you have many more equations, right? So that's a classical least squares problem, which one does, right, to get at least some solution, right? Okay, what is the approach via duality? So now I'll pick an h. The most natural choice of a convex function is, of course, a quadratic function. So we'll start with that. So half x transpose x as the convex potential. So lambda is the Lagrange multiplier. So I form the Lagrangian and I pose the problem. So it's exactly as what I showed you before. So min max of LH is now h plus lambda transpose. So b minus a transpose ax. So this is a column vector. So then lambda transpose will be a row vector. So therefore, you'll get a scalar out of this. So it's a dot product of these 2 vectors. So having done that, now I want to impose this condition to yield the DTP map is that del LH, its derivative with respect to the primal variable. Here, x is the primal, I forgot to tell you. So x is the primal variable and lambda is the dual variable in this case. So this will give me the dual, since this is quadratic, its derivative will be linear. So of course, then I can solve for it. And I can say x is equal to xh, which is A transpose lambda. So that is my map. So now what I'm going to do in the next slide is I'm going to plug this back into this. And that will define my S. So now S of lambda is the action, so to speak, is min of LH x comma lambda. And now I have solved for x from the previous slide. So I plug that in here and I get this. So now this is a quadratic form again, now but in terms of lambda, it's a quadratic form. And now max of S is the dual problem. And you set del S by del lambda equal to 0. And that will give you this lambda solution. Lambda is equal to AA transpose inverse times B. So notice now that the column space of A and the column space of AA transpose are the same. So therefore, that's important. And it will come up also in the next slide. So then the solution via duality will be just nothing but what I showed you before. So this is lambda. This whole thing here is lambda, and A transpose lambda was the map. If you recall from the previous slide, you can look at it. It's A transpose lambda was the map. So of course you have A transpose this. So that is the solution via the duality approach. But of course, everyone is familiar with least squares. So you might say, okay, what's the difference between least squares and this, right? In least squares, the solution is basically the A transpose A with the generalized inverse times A transpose B is what is shown here. The least square solution is noted is to be realized that even if the system is not consistent, B is not in the column space of A, you will get a solution. And I'll just give you an example soon, right? But as I told you before, the column space of AA transpose and A are the same. So therefore, the solution via duality will only be realized if the linear system has at least one solution. So if it has no solutions, then you cannot solve it via the approach I'm telling you before, the duality approach, whereas least squares will always give you a solution because, for instance, the example I had in mind was if you take 2 equations and you say, okay, x is equal to 2, and you take x is equal to 4, then you can see clearly that the matrix A is 2 by 1. And if you do A transpose A, essentially you'll get the average of the sum of the 1 and 1. So you'll get 2. And on the right-hand side, you'll get, like I think I picked 2 and 4 for B. So you'll get 2 plus 4 on the right-hand side. So the solution will give you x of LS will be 3 essentially. So if you pick the right-hand side to be x is equal to 2 and x is equal to 4, you'll get a solution that is x is equal to 3, which makes sense. In the least square sense, that's my solution. But that's not often the solution I want if you're solving a PDE, for example, right? If there's no solution, I don't want a solution, right? For example, right? So that's what this will provide. The dual approach will tell you that, okay, there's no solution. You cannot solve it if you dump it inside this framework.
Suku, can I ask a question?
Sure.
Before the examples?
Yeah.
So I mean, if I take a convection diffusion equation or any
Yes.
equation that doesn't fall under the primal variational framework, I can do a Petrov-Galerkin multiply, and I have a variational form, and I can solve that variational form. So,
okay.
And the complexity as I see it is less, because here you end up with A transpose A, so the condition number is square of what I would do with the Petrov-Galerkin method. So where would this be advantageous compared to
exactly.
Galerkin?
In fact, I provided this example including in the paper, because the first thing one might say is that, oh, why not do least squares, for example, right? I mean, that's
right. I understand least squares, but I said
Petrov-Galerkin also, right? Exactly, right. So I think the as I'll show you, I think I hope, especially for many on the audience, that if I show convection diffusion, it'll become clear. Or even if I show, so the point is that I want to get a strict variational principle. That is what I mean by that is that if I take the first variation of the functional that I want to minimize, or a stationary point, I should recover only the equation I'm solving and nothing else, right? It's, for example, I can give you an example like, let's say, suppose I take x squared minus 1, okay? If I want to solve x squared minus 1 is equal to 0, then I know the solution, okay? I have two solutions. X is equal to plus or minus 1. But now if I do least squares on it, for example, just since I'm on the least squares topic, right? If I do x squared minus 1 the whole square, right? Clearly x is equal to 1 and x is equal to minus 1 is also a solution of this, right? But now if you just take its derivative and set it to 0, I will also get x is equal to 0 as a solution, as a critical point, because it's a maximizer, right? So that's the point, right? Just because you are getting what you want, but there may be other stuff also on it, right? That's what I want to clarify.
So
right?
you mean the Petrov-Galerkin approach, the variation problem will introduce erroneous solutions?
It may, and also I don't know if it's not. It may not be when I say a variational formulation, I don't mean just sort of like what I proposed before, like a mixed variational, right? You can think of a mixed method, right? Essentially, I take displacement and pressure or something, right, as independent variables.
Right.
But that is just a Galerkin formulation. It's not it's like a principle of virtual work kind of thing, right? You multiply by test function and you do integration by parts, but then you have to pick spaces for that. The challenge in all these methods, right, is how do you pick spaces for displacement? If you're doing fluids, how do you pick spaces for displacement and velocity? And pressure. Sorry, yeah. And then I was mixing displacement and pressure. And in mechanics for static problems, you say, okay, how do I pick, for example, displacements and strain, for example, right? They may be independent, or if you do fully three field, you may say, okay, displacement is independent of strain and stress, but that's just a three field.
Okay, so you mean you will have constrained spaces,
yes,
as opposed to the dual formulation where you have a uniform. I see.
Yes, exactly.
I see. Okay, that's
so basically you want to get rid of this constrained space, right? Because it's challenging.
Yeah, so you don't have the Babushka-Brezzi condition.
Yes, LBB is gone, right? Basically, LBB is gone.
Yeah.
Right. So that's the basic.
Okay, that's an important consideration.
Yeah. That's, I mean, yeah, but I don't want to get into that so soon because I've not even gotten to anywhere, right? So, but yeah, it will become clearer. I think I think that's what I think just looking ahead, I think the convection diffusion is, because most people who know fluids and even otherwise know convection diffusion because it's one dimensional. It's very simple to understand, of course, right? And then if you can construct, and I'll tell you why it's a variational formulation there, right? When we get there, right? So that's why. So anyway, should I continue or? Okay, so let's take one more. Anything else or okay? Okay, so let's take one more example, which is a system of quadratic equations. So here I picked a problem which has more than one solution, just to give you a flavor of how to go about it, right? Or how to think about this dual approach, right? So let's take x squared plus y squared is equal to 3 and x squared minus y squared is equal to 1. And I pick x, so x and y, the solutions are these four solutions you have in the quadrants, in the four quadrants. So now what do I do is, so there's a slight difference from what I did before, right? So now I choose h as, again, a quadratic function, but now I have two additional ingredients, right? So I do x minus x bar squared plus beta times y minus y bar squared, where x bar, y bar is referred to as a base state and beta is belonging to R. And I'll tell you it might become clearer in the next slide, but I'll just tell you up front that what is the meaning of this stuff, at least the way I see it, right? So X bar and Y bar can be thought of as an initial guess, as a prior, if you look at the language of, Kullback-Leibler stuff, right? I mean, like a prior guess or a prior solution or a prior guess solution, because there are many solutions, right? If there are multiple solutions and you're not looking for one solution, then you might say, okay, how do I figure out, okay, how do I target one solution? Let's say if you want to target one solution, this might be a vehicle to do that. I pick X bar and Y bar, so it'll get me a solution, say in some closest sense to this point X bar, Y bar. And the parameter beta is important here because it's like you're weighting H, so that you want, as I'll show you in the dual formulation, that you want in the dual space, when you solve the maximization problem, that your guesses and your basically whatever happens bad in some sense, where things might blow up, are far away from the origin, so to speak. That's my interpretation of this, right? And we'll see what I mean by this and why this is required when you have multiple solutions, right? So, I mean, the approach is exactly the same. It doesn't change, of course. You start with the saddle point problem, which is h of xy plus now lambda 1. Now you have two Lagrange multipliers because I have two equations. So I just form this like this. I take set the same thing. I set del h by del x to be 0, but now x is a vector, x and y. So you have two equations. So this gives you again an explicit map. So notice that even if this is quadratic, but of course you have only, once you take the derivative, you get linear terms essentially, right? So that's what you get. And now you can see what's going on. At least I'll give you some insights here. So suppose you chose X bar and Y bar as the exact solution, right? Suppose you chose X bar and Y bar as the exact solution, then you know that, okay, if lambdas are both 0, essentially the Lagrange multipliers are 0, then you recover the X bar Y bar solution as it should, right? Because you know that X bar Y bar is a solution, so you should recover it. The other thing to notice is that here you can see that, oh, this guy might blow up, right? In lambda 1, lambda 2 space. So it may be unbounded. So the dual that you construct, right? The dual S functional may not be bounded, right, in some sense. So there could be degeneracies, right, in some sense. And this is also shown here. So the idea of beta is, numerically more, is to say, okay, I want to move that far away from the origin, essentially. If lambda 1, lambda 2 is 0 is my sort of guess in my Newton method or whatever I'm trying to solve it, I want to stay confined to that origin and pick a value there where it might maximize. So that's what I try to do here. So I back substitute that to form my S in this case. And notice now that S, and I just choose beta equal to 10. So I moved it far away from the origin, so to speak. And I pick one of the solutions as my base state, right? But I don't pick the exact solution. I pick one value, which is exact, and y is the right value, but 1 is off. It should be root 2 is the solution, right? And I say, okay, let me compute S. And then I actually show the plot, right? Okay, here's the plot of S, if you want to see. And you'll find that if you just solve this maximization problem, that S is maximized near the origin at this location, which corresponds to X is root 2 and Y is 1. So you recover the exact solution. But notice, of course, that as I showed you in the previous slide, that there is a singularity very far from the origin, right? And of course, you can make it very far, and you don't want your optimizer to go in that direction, right? Of course, because it might get stuck there. So you want to be close to this region, but where there is a maximizer, and it should pick it up here, for example. Because, if you do Newton, for example, it'll only pick stuff which is near where you are, right, in general.
So S,
yes.
Do you guarantee that S will be convex always?
No, it's not. It's degenerate, right? It could be degenerate, right? It could be unbounded also, right? Because if you go back here,
if it's bounded, is it convex or concave or?
Yeah.
Oh, it is. So that's an advantage too.
Yeah, that's a huge advantage, right? Yeah, exactly. Yeah. As I'll show you, right? So therefore, it has consequences, afterwards on being degenerate elliptic. So you're sure that your energy is always greater or equal to 0 in some sense, right? So you can't get negative values of, I had a slide also on the on showing you different, functions and showing you different, basically, the eigenvalues and eigenvectors and all that, but I didn't put that in right now. Okay, so the next example is yes.
Suku, maybe one question, like,
sure.
How would this look like if you made like a wrong choice?
What do you mean wrong choice?
For the X bar and Y bar, you said that you choose one that is.
You can pick 5 and 5, 2 and 1, right? Something like that, right?
2 and 1. So I was wondering, it will not be a problem that what happens if you are equally close to both of the true solutions?
Yeah, it'll pick one of them.
The model will pick
but
one.
In this case, it's but here, I mean, obviously this example is contrived, right? I just picked 2 in 4 quadrants, right? I think so, right?
Yeah.
Yeah, but of course, if you're looking for 2 solutions who are very, very close, I mean, someone, you have to tell anyone which one do you want, right? I mean, because there are 2 solutions, epsilon close, for example, right? No method can tell you unless there's something that discriminates the 2 of them, right? And that can be incorporated in the H also, right? Some features of one solution might be more, I'm just thinking aloud right now, right? It's just conjecture that, okay, if you have 2
Yeah,
solutions.
but as I said, like, let's assume that the 2 minimums are really close, and then
Come
you
again?
put like, let's assume that as what you said, like the two solutions are really close to each other, right? Like yeah, and then when you do this thing, you can still guarantee convexity if that's the case.
Yeah.
Oh,
yeah.
okay,
Yeah.
that's good.
So the trick is that you have to basically, you don't want, at least there's one thing, analysis and something is something, right? But then you numerically have to solve stuff, right? Ultimately. So then you have to look at, okay, how do I make it numerically tractable to recover what I want, right? That is the challenge, of course, right? And then you have to use numerical analysis or methods to get you there, right? So I showed you this because I'm going to show all linear problems afterwards, but just to recognize that, okay, this beta is important and X bar, Y bar are important in general for nonlinear problems, right? So and also when there's non-uniqueness of solutions, for example. So that's also is important, right? So that's just to point it out right now. Okay, so here's one more problem. But now, so this is a problem from my own work 20 years ago or so. So obviously the context is very different. So I'll just give you a broad, short sort of description of what the problem is. So, most of you are familiar with finite element shape functions, so to speak, or basis functions on a square or a rectangle or a quadrilateral, right? But even if you look at a quadrilateral, I'll show you the equations which are to be required. The shape functions are not unique, right? It turns out even for the quadrilateral, the shape functions are not unique in the sense that there are different types of what are called polygonal shape functions, which satisfy the same properties and are convex, but are not so there are infinite number of them essentially, right? So the idea here was to sort of see, okay, because I worked on polygonal methods a lot at that point, to see, okay, how do you generalize this for convex polygons, right? P. And also we did it later for non-convex polygons, but just to start with, for convex polygons, can I construct shape functions which satisfy the same properties, right? Essentially, what are the properties? They should sum to 1. The shape functions are functions of x. So the problem is posed is for fixed x belonging to my polygon, I want to find these values that satisfy, they should sum to 1, so they form what is called a partition of unity. Then their linear combination, phi1 x1 plus phi2 x2 should reproduce the function x, and the same thing for y. So this ensures that these form a basis, so they can reproduce 1, x, and y, as do finite elements. Now you impose, if you do this for a triangle, you'll get a unique solution, because there's only one solution. You have a 3 by 3 matrix here, and of course you have only one solution, which is unique, which are finite element interpolants for a triangle. Even for a quadrilateral, they become non-unique, and then that's what was sparked my interest in this problem, right? So that's basically the problem, and the problem is the linear system is underdetermined because you have only 3 equations, but you have more unknowns, and therefore in general there'll be infinite number of solutions essentially. Once you find 2 solutions, any convex combination is also going to be a solution. So there are infinite solutions for this problem. So then the idea was, what I proposed in that work is to look at the Shannon entropy, or you can think of more generally as the Kullback-Leibler divergence, where now you can think of the Wi as a prior function is a guess function. I can think of, okay, I want some solution that is very close to Wi. So similar to the X bar, Y bar, I was trying to draw an analogy to that before. As Wi is something I would like the phi to be like, but to be close to Wi, but Wi may not satisfy all my constraints. So then I look for the phi's which are closest. And obviously the interpretation here is that, which I took was that, oh, phi is like, you can think of the shape functions as a discrete probability distribution. So in the simplest case, which I did for the first paper, was that picked Wi as just a uniform distribution. So it's 1 by n vertices, 1 by n is the value. So this comes out and you get basically Shannon entropy. So minus phi log phi maximization. And if you do the KL divergence, or relative entropy becomes plus phi log phi, right, essentially. And you have 2 constraints. So now my problem is, of course, the objective function is now nonlinear, because I picked this function. Like I told you, it's a selection criteria, right? So H is the entropy function, selects a unique solution for the problem at hand. So that is basically the starting point. And then you run through the same machinery, right? Now you have constraints for those three equations. So one I call lambda naught, the others I call the vector lambda, and I basically form this. The stationary conditions are exactly the same. Del L by del phi should give you this. So for each I, this should be satisfied. Now you get rid of the lambda naught by replacing by z, which is called the partition function in statistical mechanics. And that'll lead you to basically this form for the map. So this becomes my dual to primal map. Phi IH is this exponential by sum of exponential forms. So therefore, this forms also a partition of unity by construction, right? And then you look at the dual formulation. The dual formulation is S now, is essentially this is log of Z. So log of Z is the classical sort of formulation for many entropy problems in the dual space or dual version of it, right? And then of course, you can do argmin of S, because now the original problem was maximization. Now this becomes the minimization in the dual variables in this case. So this is an unconstrained convex optimization problem. And the dual variable has, of course, only two unknowns in 2 dimensions in this case. Though, of course, you could have a vertex with 10 unknowns, right? You could have an octagon or a decagon or even more vertices, right? So that's the basic starting point, right? So this just shows you that there are other connections also to other methods where people may be using the dual approach. And in fact, if those are familiar with mesh-free methods and moving least squares, which have been very popular, there, in fact, the actual implementation is done with a dual formulation, right? It's not the primal formulation, though that was what was done, and they didn't realize that there is a primal formulation and where you can see the constraints being satisfied. And therefore, the dual formulation that they use to compute these functions does satisfy those constraints, the same constraints I showed you before, right? So that's the starting point. Okay, so now on to ODEs and PDEs, and if there are any questions, I can take a pause before starting this. Okay, let me just proceed. Since probably the time is running short a little bit, right? Okay, so let's take the strong form here. So it's a trivial equation, of course. So du by dt is AU for some time between, say, 0 and t. At time t equal to 0, I have an initial condition, u0. So the exact solution is u0 times e exponential of at. Of course, this is too trivial, but the point is that I want to construct a dual formulation for this problem, right? So I want to convert this guy into a boundary value problem, and that's the key thing, right? So let's see what can be done and how to go about it. So I let lambda to be the dual variable. Now the dual field, because now I'm looking at functions, that corresponds to the first order ODE. So the idea is simple. As before, treat the ODE above ODE as a constraint and optimize the arbitrary chosen convex potential density, because it will go into an integral, as half u squared. So kind of similar to what we did before. Like before, I was taking half x transpose x. Now I just do half u squared by the method of Lagrange multipliers. So let's see how we go about constructing it. So this gives some motivation of what are the sequence of steps, and then some rationale on choices we make, and then to make sure that they're consistent afterwards also. So consider the following function in the fields. Now there's two variables like u and lambda, primal and dual, with the dual field treated like a test function and the auxiliary function h appended to it, like what George was saying before, right, essentially. So I of u lambda is h of u, the function I pick, half u square, plus lambda times u dot minus au. So u dot minus au was what I want to solve. So that is the constraint I'm thinking of, right? Okay, please stop me in this slide and the next one if you have any questions. Okay, so this is the key two steps which I'm performing. Okay, so now I say, okay, this is u square by 2. That's what I wrote down again, plus lambda times u dot minus au. So nothing here, I've just written it now, but with h replaced by u square by 2. So what I do now is I do integration by parts on just this term, because this guy has no integration by parts. So minus a lambda u should go here, and it's exactly here. Minus a lambda u is this term. U square by 2 goes for the ride. U square by 2 goes for the ride. So only the term lambda times u dot I have manipulated. What I have done there is basically to change one derivative from u, I move it to lambda. So I do integration by parts. So if I do integration by parts here, I'll get lambda times u on the boundary, which gives me this term minus this term, right? And then minus lambda dot times u. And that is exactly here, minus lambda dot times u. So that's the integration by parts goes from here to here. So now let's see what I get. So now I know that u of 0 is u0 from the initial value problem, right? Data is telling me that the initial condition is u0. So I put that here. And then I have ut times lambda t is equal to this exactly. So I just repeated that myself, right? So now I'm going to do something on this term, which will become clearer after a few, probably the next slide, but I'll tell you what I'm going to do now with that. So now what we do is we omit the term u of t times lambda of t. So this choice is motivated by the design consideration that the Euler-Lagrange equation of the variational principle that we obtain should recover the primal problem. And we refer to the functional that results as L with D, with this expression, right? Choosing D is equal to this in the notion of Lagrange density field theory is where you have now lambda and lambda dot are independent variables when you think of the the Lagrangian itself. And when you take the Euler-Lagrange equations, so therefore I denote that by this capital or the script D. So think of L of u lambda is equal to L, the script L or calligraphic L dt minus u naught lambda as 0. So what I've done here is to just take this guy as my calligraphic L, and I've knocked off this, right? So I've taken this to be 0, knowing that what I want afterwards should correspond to the Euler-Lagrange equations of what was posed, right? So that's the objective. Okay, so L is the Lagrangian density for the primal dual problem. So what do we require now? Okay, the same idea, right? Again, del L by del U, the derivative of the Lagrange density with respect to U must be 0. So from here, you can see what you get. So just to show you here, right? So the derivative of this is a U. That's this U. The derivative of this with respect to U is this. So that's why I put U outside to see the derivative very clearly. So you get a minus lambda dot minus a lambda, which is precisely this. So now you have this map for all D. So this generates the mapping from this space to UH of D. And that is what is given here. So now I say, okay, so there is this mapping between lambda and U in this way, which I obtained from this is lambda dot plus a lambda. Okay, so I have this magical mapping, so to speak, lambda dot plus a lambda, and we're going to use that subsequently also. Okay, so now I basically go back and say, okay, what is my S? S is nothing but if you plug this into this expression here, you'll get precise. If you plug this inside here, you'll get exactly minus UH squared by 2. So that's what you'll get, minus UH squared by 2. That's what you'll precisely get, minus U naught lambda, noting that I've, of course, knocked off the first term, right? So this can be written as L of UH minus this. So I've defined this as L again by plugging in UH instead of U there, right? So this is the dual density is given by this expression. So now you can see that the strong form of the IVP can be expressed simply as UH dot is equal to AUH. Very similar to the linear problem I was telling you, right? When I said, oh, G of UH is equal to 0 is the original problem. Here the map dot is equal to AUH T with some abuse of notation here, but just to show you that, right? And now the point is that I need to show you that, oh, actually, this is a busy slide or a busy information here, but I'll just take you step by step, right? To show you that, okay, if S was the variation, if S is the action, then least action should give me back the problem I posed or the problem I want to solve, right? And let's see if that happens. So I take the variation of S. So the variation of S is essentially del L by del D times is the variation of D, where D consists of these two guys, right? So now what do I do there? So then if you go back to I'll just point it out here. So the variation of this, right? The variation of this will give me del lambda dot plus a del lambda. That's what to be kept in mind. So if you take the variation of this, you'll say, okay, what is the variation of this? It's minus 2 by 2 UH times the variation of UH, which is what I just told you just now, right? Del lambda dot plus a del lambda is the variation. And then UH is appearing there, right? So UH times the variation of that is this expression, which is exactly here. Now you do integration by parts here to move the del lambda dot to del lambda, to move this guys to the other side, right? So that's what you'll get. So minus AUH del lambda remains from here. So this I do integration by parts, right? So this I do integration by parts. I'll get one term on the top boundary, which is I'll get basically one term which looks like UH at time t times del lambda at time t, which I remove for now by imposing the condition that del lambda of t should be 0. And then I'm left with this. But now if I apply this, I use the fundamental lemma of calculus of variations, I will get that, oh, this must be satisfied and this must be satisfied precisely. And this recovers the strong form and this recovers the initial condition. So this is what I meant is that the variational principle should recover exactly what I want to solve. And that is what it does. So if I say 0 is equal to del S for all del lambda, proviso that del lambda of t is equal to 0, right? That's the condition I impose while coming here. Then it implies star. So it implies this equations. And now you can see the rationale that in some sense I'm saying, okay, if lambda of t is prescribed, then its variation should be 0, right? So therefore, it should not appear in my functional. It's very similar to primal variational problems I showed you in the slides 2, 3, and 4 or 5, where I shared, okay, if the value is in your space, if u of 0 is given to you as 0 in my space, u of 0 doesn't appear in the functional. So that's to be kept in mind, right? So that's basically the same rationale which we use here, right? So, okay, now what happens? You plot this.
So you're saying that if you would have kept this u of t and lambda of t, you would not be able to recover the problem, right?
Exactly. Yeah. But it's no different from primal variational problems that we are all used to solving, right? When we solve, I can go back, in fact. Let me quickly go back just to reconnect it, right? Oops, sorry. So you look at this variational problem, right? Which is what we are all used to, and for everyone's used to this, right? So trivial problem, right? So in this variational problem, u of 0 does not appear, right? Because we know that the variation of del u of 0 is 0, right? And u of 0 should be in the space. It should be in the definition of the space, right? So how can it appear again in the functional, right? That is the rationale. But this is we do this automatically without thinking, at least when we do these problems, right? We say, okay, u must be in the space, blah, 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 right? But here what we are doing is the reverse engineering. We are trying to construct a pi, right? It's basically the inverse problem of variational calculus, right? In some sense, right? You can think of it like that. So that's why this is what I...
Suku, then we need to find a space for lambda,
yes,
which has this variation at t 0.
Yeah, I'll discuss that now.
So in a complex case, that may not be trivial.
No, but lambda is just, the other thing that comes up is that lambda of t has to be prescribed to be 0, right? Essentially what I say, what I picked here.
No, I know, but I mean, this is for this problem, but I could see that that this could be a problem in general.
No, but in fact, it gives flexibility because, it turns out that lambda of t can be any value. Because, the variational calculus tells you that if lambda of t is any value, its variation is 0, right? By construction. So it won't appear in del S, essentially, right?
Right. But if you in multi-D, it's not a value, it could be a function.
Sure,
so you have to prescribe a function.
Yes. Yeah. But the point is that, 0 is the simplest function, of course. But you have the flexibility of choosing lambda, right? And I show you, in fact, 2 examples now. One with a 0 lambda and one with a non-zero.
But you do need to have a consistent space that satisfies that condition, right?
Yeah. But it's very similar
when
to...
you discretize lambda.
Yes, exactly. Yes, very similar to when you say, oh, I want to solve the Laplace equation or the Poisson equation in, classically, right? With a variational principle, I say, oh, use G on the boundary, right? So of course I have to satisfy...
Right, so you can do some lifting or something.
Yes, exactly. Yeah, lifting, right? Basically, yeah. You can. The same ideas, basically. But the what appealed to me, of course, was the whole thing of, given my previous work on boundary conditions and entropy and all that stuff, right? So that's what, right? Anyway, let me proceed. Okay to proceed?
Yeah.
Oh, okay. So I think it'll become clearer once I get to some examples, I think so, overall. So now the nice thing is that when you substitute the DTP map, right, then what happens is that this becomes the boundary value problem. So you can see that the first order initial value problem becomes a second order in time boundary value problem in terms of the time, right? Of course. So lambda dot double dot minus a square lambda is equal to 0. So it has an exponential form, and we go over some more details in the paper. So you get a Robin-like boundary condition at 0 and the terminal boundary condition. So you have an end condition, a boundary condition on lambda t, I call it lambda subscript t, which is an elliptic problem in 0t for lambda, and this is arbitrarily chosen. And that will become clearer by this statement. So of course, the reason why the condition can be imposed, of course, in the primal problem, we don't have something, there's no, we don't know where we're going, right? So we don't know what the value is going to be afterwards, right? But the map, there's gives you the insight, right? So the map is basically lambda plus a lambda, lambda dot plus a lambda. So at the terminal time, you should have lambda dot at time t plus a of a times lambda at the terminal time t must be satisfied. So even if you specify lambda t by some value, lambda dot t can adjust so that you recover the unique value of UHT. That is to be the exact solution. So that is the flexibility it provides. And we show that actually in the paper, and I'll show it to you subsequently in the examples also, right? And in the paper and the appendix, we also show that, if you just do a very weak form of this problem, right, it may not be apparent at all that, just by looking at it, you won't see it, but there's some tricks here to play some manipulations, right, of the integrals that appear, that the weak form of this is precisely del S is equal to 0. They are both identical. It should be, of course, identical, but it takes a few steps to show that equivalence. Okay, so now let's get to convection diffusion. Before we run out, we already sort of, should I continue? I'm gone very slowly, I think so.
No, please continue.
Yeah, because I didn't want to, I cut down my slides, but still there are quite a few.
No, it's good. It's good pedagogical. It's good for everybody. Thank you.
Oh, okay. So obviously this is the crux of the problem, and the question you raised, right? I mean, if one has to understand this clearly to say why and where it is distinct from a Petrov-Galerkin or a Galerkin or any other least squares or any other method, right? Okay, so I'm solving this well-known problem where alpha is the Peclet number, and you have this sort of exponential solution. And of course, as alpha gets larger and larger, you get a boundary layer near the right end, and it gets more and more difficult. So then you have to use some upwind scheme or SUPG or something in a Petrov-Galerkin setting to solve it. But of course, we want to use the Galerkin method and just run it with some approximations to solve this problem, right? So that's the problem. So now, of course, the starting point of this is to convert a second order PDE or ODE into a system of first order equations. So let's do that first, right? So I'm going to call U and Q to be my primal fields that satisfy the two first order equations. Q prime is equal to alpha Q and Q is equal to U prime. So if Q is equal to U prime, and Q prime will become U double prime. So U double prime is equal to alpha U prime. So exactly the equation I was solving before, and I introduced this sort of intermediate variable of field Q to aid me in the construction. But subsequently, all the steps I'm going to do is mirrors what I've done before. There's no difference really. The steps are identical, right? So again, I had to pick now H as a function of U and Q. So the natural choice is, okay, let me just pick half U square plus Q square.
So sorry. Yes. So any high order PD that you have, you need to make it first order, system of first order.
Right. Or if you have, make it first order to introduce, because you can introduce more variables, right? You have freedom to do all that stuff, right? I mean, you can introduce more variables to basically reduce the order, because the trick is to play this integration by parts trick, right?
I know, but you could do it with the high order, integrate like you showed the biharmonic. Why do you need to always make it first order system?
No, but if you do, for example, if you do biharmonic, right? Then you have to introduce two second order.
Yeah.
Oh, you don't know, you meant right down to one order.
Yeah.
No.
Not necessarily, okay.
No, I meant second order, if you have a second order PDE.
Yeah. So the fourth order will become, break to second order.
Yes, exactly.
Okay,
so it's very similar to a mixed method, what one typically does in a mixed method, right?
Okay.
And then proceed from there, but of course with this different twist, with the convex potential guy coming in, right?
Yeah.
That's the basic thing, right? Okay, so now I can probably go a bit faster, because I sort of told you the machinery, right? In some sense, the same tricks, integration by parts and all that, right? So I'll just tell you in words, but not go through every equation here, since it might take too much time, right, overall. So the idea is the same. You start with H here, plus the two constraints. But now, just to point out, I have lambda and mu as my Lagrange multipliers, which corresponds to the first equation and the second equation, right? Again, I just do integration by parts. I'll get two boundary terms. So notice that, just to point out at least one thing. So Q prime lambda is what problem is the term I treat by doing integration by parts, right? That's why you'll get a Q times lambda prime here. The minus will go off, right? And then here you have U prime times mu. So U prime times mu will basically get switched to U times mu prime, right? Minus U times mu prime. And then you get two boundary terms which correspond to these terms, right? So that's the basic idea, right? And then you say, okay, we'll incorporate the boundary conditions. U of 0 is 0, which is what is given, and U of 1 is 1. And now again, arbitrary. The lambda guys are arbitrary, right? You pick the values. Lambda 0 and lambda 1 is 0. I pick them both to be 0, but they can be arbitrary to make LH becomes this. So LH becomes this. And then afterwards, I define exactly as before, L of this is this. And now my D variable D field has expanded to these additional in the Lagrangian density definition of both mu prime, lambda, and lambda prime. So all these are independent. When you take variations, you'll get variations of del U prime, del lambda prime, and so on, right? It's very similar to how one does, mixed variational principles in general. So now you set del L by del U is equal to 0 and del L by del Q is equal to 0. And we obtain this map. So U is mu prime and Q is mu minus alpha lambda minus lambda prime. So that is the map now I have. That is the DTP map, is the dual to primal map is given by this. Okay, so now what happens to the Lagrangian? The dual functional can be written as this. S of lambda mu is this. And so you can see it has the structure is similar because of the choice of H. So again, you get minus half U square H plus Q square H dx plus this mu of 1, which is that term which is left over. And now if you want to plug it, you see, okay, what is U of H? It's mu prime. And what is Q of H? It's mu minus alpha lambda minus lambda prime, right? So of course, you take its first variation, and then you can basically take its variation with respect to lambda and with respect to mu, and then you can discretize it, and you can get your linear equations depending on what you solve, right? So let's start off with, before starting off, I should obviously mention. So there's a lot of work already done by Amit and his co-workers and his students on transient heat conduction and linear transport here, on Euler's equation for a rigid body, double well potential for nonlinear one-dimensional equations, elastostatics, and also inviscid Burgers, both conservative and the Hamilton-Jacobi form, right? So this was all done with FEM as the basis, or FEM shape functions, and for simple problems in general, but just to illustrate the idea and just to point out what is the key thing that one must recognize. With FEM, what he had to do was that because U is mu prime, right? U is mu prime, and we are discretizing, important thing to recognize is we are discretizing mu and we are discretizing lambda, right? That is what because S is a function of lambda mu. I've forgotten U. I've forgotten U and Q is gone. It's not even there, right? When I solve this problem, it's a post-processing step to recover basically U and Q, because once I know mu and I know lambda at every point, I know its derivative, so I can find out U and Q explicitly. So that is the approach wanted to use. But of course, now you recognize that, okay, if I'm discretizing mu and lambda, but U is equal to mu prime, then the first observation is that if mu is only a C0 function, right? It's a finite element basis, which I showed you, the hat functions, then U will be discontinuous, right? U prime will be discontinuous. So of course, if I want to recover a continuous solution, I have to do some L2 projection of my solution at values, at the nodes. So that's what he had to do in his papers. So basically use an L2 projection of that to recover or to plot, for example, if you want to plot the solution of U, you have to do that, right? But the basic idea is still valid, as I'll show you afterwards, that because the integrals that appear have only one derivative. So you can use the C0 function, right, to discretize it. So that's the power of it also, right? You can use C1 or C0 depending on the nature of the problem you're solving, right? But let's start with an even trivial example, right? And that's why I would like to understand problems when you go down to the basics to really see, okay, what is going on, right, in this. So I take obviously a very, very simple problem as U double prime is 0 in omega 0, 1, and U of 0 is 0 and U of 1 is 1. So the solution is X. Of course, why would one solve this problem at all with this, right? But just to understand what's going on, I think it's beneficial, especially if you're new to this, to see, okay, what's going on. Okay, so now I say, okay, use alpha is equal to 0 in my DTP map before, because the derivation is exactly the same, because the problem is the same. I've just dropped the alpha. I've said alpha is equal to 0. So the map is mu prime and Q is mu minus, so this is 0, minus lambda prime, which is mu minus lambda prime. So the form of S is identical to before, to the same thing. And now you're subject to these conditions that lambda must be 0 at X is equal to 0 and must be 0 at X is equal to 1, right? And this is what I have. If you want to plug it and find out the Euler-Lagrange equations of this problem, you will find out that it's mu prime minus lambda double prime is 0, which is mu double prime is this. So the dual function, the dual equations you're solving are really mu triple prime is 0 and lambda 4 primes is 0. So this is basically a fourth order for the lambdas and third order for the mu, if you want to think of the equations you're solving, right? Ultimately, right? Even though the primal forms the dual forms are different, right? Think of, okay, so what do? So I first solve it with just function polynomials. I say, okay, what happens if I just choose? So knowing that the dual, the space, right, is, I know that this is 3 derivatives, this is 4 derivatives, right? So I know, okay, can I recover the exact solution, right? So then I say, okay, let me choose a quadratic function for this guy, right? So the third derivative will be 0, of course, and then, so it satisfies the governing equations, of course. So I say, okay, can I find out the coefficient so that it gives me the exact solution, right? So then I chose lambda theta to be basically 0 at the end. So that's how it satisfies the boundary condition. So at x is equal to 0 is 0, at x is equal to 1, this is by definition 0 for any b0 and b1. And there's nothing placed on mu, so this can be arbitrary. So a0, a1, a2 are all arbitrary. So now what we do is you plug this into the functional, right? You plug this inside the S guy. So this becomes then a quadratic function in a0, a1, a2, and you take its derivative with respect to these coefficients, it'll become a linear system of equations, right? It'll become a linear system of equations, and I did it symbolically, everything. So you get precisely these equations, right? So this is a matrix, this is the right-hand side vector, and this will give you a solution of this. Okay, now what does this give you? This gives me the solution for the dual fields as 5 by 6 plus half x squared. Lambda theta is this, right? Because this is a quadratic function, so it's picking the best choice. That's what variational principles do, right? They pick you the best choice of coefficients in the space. That's what mu theta is, and that's what lambda theta is in this case, right? These are the best two choices, right? So let's see what it corresponds to. Oh, it corresponds to u theta as mu prime. But what is mu prime? Mu prime is x. And q theta is mu minus lambda prime. And you can see from here, you'll find that it's equal to 1. So of course, it should recover the exact solution because I have chosen ansatses that lie in my exact space, right? They span the solutions in the exact solution, right? So therefore, you must recover the exact solution if you have a bona fide variational principle. That is what happens. But now what I'm going to do is, in the next step, to going back to what George's point is that I can, just to show you also that, okay, I can change the boundary conditions on lambda, but this does not change. So in the dual fields, I can change the boundary conditions here, but the flexibility is that it does not matter in the solution itself, right? So to that end, what I'm going to add is I'm going to add an arbitrary cubic function here. So if I add an arbitrary cubic function here, notice that you take its square and you take its derivative, it will only appear as constants in my linear system of equations. So it will only impact the right-hand side. So that's what I wanted to emphasize before showing you the equation. So this is my right-hand side, but this is the extra addition I add, right? So now you can see that at x is equal to 0, this is 0. But at the x is equal to 0, this is 1, right? So these are all 0, this is 1. And at x is equal to 1, this goes off and you get 2. So now my boundary conditions are lambda at 0 is 1, and lambda at 0, lambda at 2, lambda at 1 is 2. Again, we do the same thing, nothing different. Left-hand side has remained the same. My right-hand side coefficients are changed. Of course, these solutions has changed. And of course, this solution has changed. Mu is 11 by 6 something. This is, again, a cubic function, which is something else. But the solution is recovered is exactly the same as it should, to demonstrate that indeed it does not depend on the boundary conditions you impose on lambda. So those are arbitrary in some sense, right? So that's what happens. So now let me show you a few things with, at least let me finish with, I'll skip the time dependent. I have some results there, but it's just a few slides. But I'll just show you a quick overview of the neural network approach and also the B-splines, because they're the simplest to understand, I think so. So the same problem I looked at, and now I took so because I would like smoothness in some sense, right? Because then you don't have to do any projections, right? You can just do no need of L2 projections. So essentially, I said, okay, let me use RePU functions, which are powers of ReLU. And then I basically want to just use essentially only one hidden layer where I fix the bias and weights. So only the output layer is unknown. So it's like a Galerkin approximation in some sense, right? So I use linear activation for the output.
So just 1 second. So this RePU is basically hat functions that Jin-Chao Xu introduced,
yes,
which can be written, of course, exactly in terms of ReLU.
Yes, yeah, right. So I just use powers of basically these RePU functions, linear combinations of them I'm going to use, right, essentially. Okay, so then I choose, the point is I want to, unlike traditional pins or traditional neural networks where everything is, obviously you're solving it via training, right? The values of the bias and weights. So what I do here is I fix the locations. I fix the locations, right? When you have basically, Wx plus B, I'm fixing the B in some sense. I'm fixing the B and I'm also fixing the W's. I'm fixing them to be, say, 1, for example, or -1, depending on the context, right? So I'll show you the pictures before, which might clarify the rationale for this approach, right? So I want to fix that, and only the output layer has unknowns.
So it means, so you're only solving the linear.
Yes, exactly.
layer.
Right. I want to have a parallel to what I've done before, and also just to understand what's going on, because I'm going to use B-splines afterwards, right? And to just understand, okay, does it make sense, right? What I'm getting, right, overall. Okay, now this is a bit a mouthful, right? So what I did was to think of this, okay, you can think of at every, so I call these knot points, right? These locations, what is used in like B-spline theory, right? So you can think of, okay, I want to construct basically an inverted hat function. Like I want to construct an absolute value function at every Gauss location, at every knot location, right? For that, basically, I want to get one ReLU. You can think of just, if you want just to think of ReLU for now, P equal to 1. One ReLU going to the right and one ReLU going to the left. So then you can think of x minus xi and xi minus x as two guys, right? Which are the companion sort of functions, right? So we know that if you just add both of them, you'll recover absolute value of x, right? And if you take the difference of this and that, you'll recover x itself. So of course, then we know that the span of these functions should reproduce constants in x, right? Because 1 minus x plus 1 minus x will give you 2, for example. You can get a 2, for example, from the outer functions, right? So the I is equal to 0 function and the I equal to n function are global. They live everywhere. But all the interior functions have compact support, right? But of course, as the number of n increases, the compact support decreases, right? As we know, right? But then what I do is I want lambda to be 0 at the ends, right? But I know that these guys are 0 at x is equal to 0, and these guys are 0 at x is equal to 1. So then I just use a convex combination of them, right? I use a convex combination of them to knock it off. I could have also just multiplied the whole thing by x times 1 minus x, but I wanted to make it more efficient to minimize the number of, I don't want to make this higher order in some sense unnecessarily, right? Just to use the minimum possible, right? 1 minus x times this plus x times this, and then now I have basically a lambda that is conforming, that is admissible, that is in the right space. Because now my lambda is a function that is smooth, okay, but it's at least C0, and its value at both ends are 0. So that is the starting point, essentially. And I use, again, symbolic computation, so everything is exact, right? Whatever computations I do are exact. And just to give you a flavor of how it looks like, so these are for example, for p equal to 2, these are the Jinchao functions, right? Which are basically powers of ReLU, right? Powers of ReLU in one direction and the powers of ReLU in the other direction. Of course, I don't use this other guy because it's less than 0. So it's not going to take part in the location, in the computations, right? So these are location of knots, right? And these are for q equal to 3, and then you can think of other versions, right? So if you use alpha is equal to 1, which is obviously very simple, this is the exact, so that's what I'm going to show in a lot of my plots. Left will be exact typically, and right will be the numerical solutions. And also I'll show you errors to get a sense of it. So these are just 10, basically 10 unknown functions. N times 2 is 20 total because you have lambda and mu. And then I use p equal to 2 and 3. So you get accuracies of, on the order of 10 raised to minus 4 and 10 raised to minus 4 for both u prime, for u and u prime. So notice one thing that here, in fact, it delivers better accuracy often in u prime than u. Obviously, I'm using one order higher often for u prime, but the accuracy tends to be better because you can control the accuracy, essentially. I'll show you afterwards some convergence rates, right? So again, now if you go for a higher order, 3 and 4, you can see, okay, you can get better accuracy and so on, right? Of course, with alpha equal to 10, it's more difficult. So p equal to 10, the errors are obviously not so good, but then if you increase it to larger values, you get better errors, right? Of course. So of course, with 50, the boundary layer gets very sharp here. But even with 2 and 3, it's not so good. But with larger values, it gets better, right? Overall. But I stopped it here because I was going to use B-splines to illustrate, because there you have more control of it's sparser, and then you can use more. You can go to higher orders also, right? For example. So okay, so then just to go to B-splines, and many of you are familiar with CAN networks, so you can, in a loose sense, you can think of it as a shallow network with CAN, for example. So that's why you introduce the knot location, because I'm going to use it again here. But now I'm going to repeat the knots. So basically, you can repeat the knots to get interpolation with higher order B-spline functions, right? So that's what is shown here. And now you construct smooth approximations for dual fields. So this is the approximation for the dual fields. So for mu, there's no constraint. So I use all the functions there. But for lambda, I knock off the first one and the last one. So if you notice here, I did not choose I equal to 1, and I don't choose n plus q, right? So because the first one is 1 at the x is equal to 0, and is 1, the last function is 1 at x is equal to 1, like FEM functions, right? Because the repeated knots, you get interpolation there, but the smoothness decreases there, right? So that is met. So now this approximation is kinematically admissible and it's kosher, right? Basically, right? So then I just solve it for 50 because for lower values, it's clear that all these methods will work very well. It's the challenges when you go higher. So obtain for varying P and Q. And just to show you that, and I have not shown you, like in case you're wondering, oh gosh, where's the stiffness matrix and force vector for these linear problems, right? So in fact, it's given the whole bunch of equations for transient convection diffusion is given in the paper, but it reduces to these equations for the problem at hand. And what to observe is the following. First of all, so K is symmetric, clearly here. So K lambda U is K mu lambda. So in the lambda U space or mu space, it's a symmetric matrix. So for this equation, you get a symmetric system of equations, and there's also a positive definite, it turns out to be, right, in this case. So you'll get a unique solution as long as your spaces are admissible, of course. That's the caveat, right? And you don't choose basis functions that are dependent and all that stuff, right, in general. So you'll get a linear system of equations that is invertible and so on, right? And it's symmetric and positive definite, so therefore you're guaranteed a solution. And that's the nice part about this, right? So I'm solving, going back to what George was asking in the beginning, is that now I have a Galerkin method. Okay, there's some extra cost. I have to discretize lambda and I have to discretize mu, two fields. But I can use a standard Galerkin method, of course, in general, right? So that's the benefit of this, right? And to show you what these functions look like, I just plotted a few cases. So this is for p equal to 2 and q equal to 3 with n equal to 20. So you can see that on the left, for mu, I have this function, which is also at 1. And on lambda, I knock off the first guy and the last guy, so they don't appear, right? So that's why only the internal functions are appearing as unknowns. So these are the unknowns for lambda, and these are the unknowns. So the number of coefficients will be exactly the number here, and exactly the number here that you solve for, right? So with alpha is equal to 50, then you can increase. So I start with p equal to 2 and 3. Then I can go to 5 and 6. And you can go higher also, of course. I've gone to 7 and 8, for example. And you can get varying accuracy, of course, with this, right, as you go. And then the lastly I show you is the convergence study of this problem. So you can go right down to the bottom and actually plot the convergence rate. And of course, it's very slow because it's, the errors are still large. So notice that the derivatives go up to 50. So when you compute the relative L2 norms, right, it should be kept in mind that, the burden on the derivative is much larger than on the u function itself, right? So this is p equal to 1, and then if you go to higher order, you get basically, for 2 and 3 and 3 and 4 and so on, you basically can get more accurate solutions. And here you observe that it's p and p plus 1 and u prime, essentially. And that's just using simple, convergence theory or a priori estimates of this Galerkin theory, essentially, to reach at this conclusion, right? Because p is equal to 2, so typically you'll get p plus 1 in L2, but because u is mu prime, you lose one order, right? Basically, you'll get only p here, and I'm using q's 3, so it's one order higher. So that's why I get p plus 1 here.
Yes. How come the L2 error is higher than the H1 error?
H1 is higher, right? No,
the L2, you show the L2 is higher than the H1 error. That's not possible.
L2 error.
Look at your legend, blue and red. Maybe you mislabel.
No, L2 is H1 is more accurate.
Why? Oh, you said that earlier, right? You said the u prime is more accurate.
Right.
Yeah. I see.
Yeah.
But it's it's a semi norm, not the H1 norm, because the H1 norm will have the L2, which would be okay.
Yeah. It's a semi norm.
Yeah. Okay, good.
Yeah. Okay, I'll probably skip this because it's essentially the same thing, but now you have time and space, and I don't know, I've gone already 20 minutes over, right? But the basic idea is the same thing. Now I just use tensor product B-splines to solve this problem, and just to illustrate the idea, right? I just use a single slab. So I go from 0 to 1 in one shot, but of course, normally you would take time slices and proceed in time, of course. But just to illustrate that, okay, this is the exact solution. It's a very simple problem. right? It's not super difficult, of course, but even with this simple problem, you can just use like 50 odd unknowns, and you can get errors on the order of 10 raised to -3 or thereabouts, right, with this problem, right? That's the illustration, but there's more details on this and time slicing and the issues of, the errors on the boundary, and, there are a lot of other details which we have discussed in the paper, but I've not shown you the, in some sense, I've not shown you the formulation of this problem, so I don't want to go off on a tangent at this point. And you can ask, obviously I can answer questions, but just to give you a quick overview of the whole talk. So I've given you at least, I hope I have given you at least a general idea of how to construct a variational principle that do not have a variational structure in primal form. For PDEs and ODEs that don't have that. And the key ingredient in this approach is that you treat the given equations as constraints. And if you have a second order PDE, you think of it as two first order PDEs and then think of it as constraints. But the flexibility is really in the choice of this potential, right? That is how you can pick based on to dominate the nonlinearities in the problem. And the nice thing is that you only end up with Dirichlet boundary conditions on dual variables. And in fact, you can use zero Dirichlet boundary conditions on dual variables, which is even nicer, of course. And in the paper, we discussed the degenerate nature of the equations that arise if you have, for example, transport and other things. And at least I showed you this, that you can control the error if you use convection diffusion, and I just glanced over heat conduction, and there's also transient convection diffusion in the paper. And what's interesting is that at least, of course, the natural extension is for nonlinear problems, but I'm also very interested in looking at, trying to think of the pin problem itself via duality, which is really cool, I would say, right? If one can do it, of course, right? But that'll be very interesting for some future work, right? Okay, let me stop here. I can take any questions.
Great, thank you so much, Suku. This was a really nice presentation. Do we have any questions from the audience?
I realized it was a lot of stuff.
Yeah.
Let me ask one more question, and then some people will think about other questions.
Yeah.
You could use spectral elements like Hermitian spectral element instead of B-splines to get better accuracy, right?
Oh, you
and also to get sparsity and so on.
Yes. Yeah.
So there's a
there's a whole slew of things one can do. Right?
But there's no advantage of going into neural networks because you'll end up with non-convex.
No, that's what I mean. That's what the pin problem is. The fundamental training problem is still there.
Yeah, optimization. So
yeah, the optimization, that is the killer, right? I mean,
here you are.
Yeah, but the point is that the notion is that if you're solving, for me, like if you're solving like dynamical systems and things like that, right? I mean, at least it tells you something about, it gives you more a construct, right? Which is not there right now, at least, right? That's my perspective, right? And also, I mean, smart people are working, if they work on it, they'll come up with other ideas, right? Which are nice, right?
That's very nice, yeah. Thanks for the pedagogical approach.
No, because I thought that, it's like, if I just talk about just like a presentation, it'll get, if you don't understand primal variational problems, how can you understand dual variational, right?
That's right, yeah. They're supposed to take the courses, but they
no, because I know often, because I presented this at one place else, and often I people get confused that, they think that I have to also discretize U, the primal. But then I said, I missed my point. I gave a bad presentation, I thought, right? Then, because I did not convey that always that you have to, I'm only discretizing lambda and mu, right? Only the dual. Right. And then I just recover like a post-processing, I recover the primal functions, right?
And you solve an unconstrained problem. That's
yes.
At the end, you solve an unconstrained problem, which is
the big deal.
Almost convex, let's say.
Yes, almost convex. Right?
Yeah,
but not strictly convex.
Yeah,
right.
But how would you incorporate data then? If you have data, I mean, it's the same problem that.
Yeah, but that is fundamental to. That's why neural networks are powerful, right? Inverse problems and data and all that, right? But the point is that you can incorporate it, but at least you can think of everything through duality. Is my idea, right? I mean, that's the notion that, because now you think of, I mean, often, probably if you think of, like normal training, for example, and like L2.
Can you put in the Lagrangian? In the Lagrangian? Can you put in the Lagrangian an extra term?
Yes.
For the data?
Yeah, you can.
Because then that would be an advantage compared to classical methods, because we cannot incorporate data in finite elements. But here,
yeah, you can. You can incorporate as a constraint, of course, right?
Yeah. So yes, as a constraint, as an extra constraint for the data in the Lagrangian, and then you have to take I mean, you have one more
Yeah.
Just like you have the two.
Right, but that's why if you have any approximation, right? I mean, because in some sense, like u at 1 is equal to 1 is a data like thing, right? I mean, when you have a boundary condition which you're not imposing strongly like what one does, right? It's like it's like another data sort of, right? Oh, I know that u of 1 is 1, right? But it's not being imposed strongly, for example. Then you think of it as data also, right? So you can think of it at least as data, though it's not real data, but it's PDE boundary data, right?
That's true.
In that context, right? But I'm thinking more generally that you can think of whatever constraints you have, linear inequality constraints, a lot of things can be slack variables you can introduce, I mean, it opens the door to, classical methods, new formulations, right, for classical methods, but also, because my sense is also that even for like networks, right, like if you're, okay, the point is that if you're solving, like say convection diffusion or anything that has convection in it, then you're kind of constrained by, okay, kind of I have to use the strong form, right? So then, at least here, if you use the weaker form, then if you don't have second derivatives, you need only one derivative, right, so to speak, right, in the solution space. So you have, so if you think of, okay, speed of computing derivatives, you don't want higher derivatives in, networks, and because it's fast, it takes more time and, costlier, right? Yeah. So, I mean, there are other connections.
I think the jury is out in terms of trade-off of accuracy, computational speed.
But I mean, I'm saying in general that, but I focus more on accuracy and robustness, right? So that is my at least viewpoint that, things get faster and better with time, and algorithms might improve. But fundamentally, if a method is not robust and you cannot deliver improved accuracy, then there's always a doubt, or that can you get a better solution, right? That is the question. That is the key, of course, of all of numerical methods and computational methods, right? Yeah.
Hi, it's Jacob here. I'm a PhD in electrical and computer engineering at CMU. That's a nice talk. Thanks for the great talk. And I have a question on the problem, like formulation that you have. It seems to me that you're solving a primal problem by formulate into a dual Lagrangian problem with a arbitrary chosen auxiliary potential, like a function here. So my question is that by introducing this like auxiliary function, are you actually solving like a PDE constraint optimization problem, or I want to also get a sense like what is the connection here to say a PDE control problem? Say you have PDE constraint and you actually optimizing over something. Like can I replace the potential here with something I actually care about and instead solve a optimization problem?
Right. So actually, this brought me to, there are many things we mentioned in the paper. One is the connection to, of course, least squares, and the other is to adjoint methods, right? I mean, but the connection to adjoint methods is a bit loose because, I mean, if you look at, minimizing drag or something in, like aerodynamic flow or something, right? Then there, the notion is different, though you get the adjoint equations are very similar to what we have done actually with this equation, right? This is a step. But of course, their purpose is different because you're trying to minimize something which is given to you. I want to minimize this. Here, H is entirely my construction. Right? It's entirely my choice, essentially, right? What I do. But you're right that there are some very nice connections. It's got deeper connections to gauge theory, for example, which is some of Amit's papers also. And there's also nice connections to probably, game theory where they, solve Fokker-Planck and Hamilton-Jacobi. And, there are all these optimal transportation and, it's like, all those weird, I mean, much more deeper mathematical analysis and functional analysis topics, right? So there are many, many other connections that may exist and probably do exist, but that's beyond, But yeah, you're right. It's like a constraint problem essentially, right? But,
I see.
the difference is that here I'm not given H. In many problems in PDE constraint, you are given what is to be optimized, right? So here I'm choosing it. My analogy would be more like when people like what is in the ML literature that or in just ML broadly, right? They look at for the training, they say, okay, you have a loss function which is mean square error loss, right? But then they add like a regularization, right? L1 or L2 or something, right? So in some sense, that is their H, you can think of it, right? Because they have these constraints at all these points, right? Essentially. But then they say, okay, I want to make my problem better in some sense, right? I want the weights to be bounded and not blow up. I want sparsity, I want L1, I want only few W's to not be non-zero. So there are all these things. So you do L1 or L2 and it gives better solutions, right? No, not surprisingly, of course. So
thank you so much for
maybe-
the explanation. Maybe a quick follow-up question is that
Yeah.
I believe you're using like productive functions in the examples. It seems to me that say if my goal is to try to just stabilize the PDE, then I can probably just increase the weight of those auxiliary productive function, and I essentially solve a PDE control problem in this sense.
Yeah,
Is that correct?
Yes,
Gotcha,
yes.
gotcha.
I mean, you can. That's why the nature of the H you're talking about, right?
Mm-hmm.
Yeah. The nature of the H depends on what you're solving. For many problems, just using U square or V square or Q square is sufficient, right? But obviously, not for all problems, right? I mean, if it's highly nonlinear and dominant, right, then you have to basically figure out what to use based on experience and what people have been using. Because in every PDE right now, the literature has a lot of information on the nature of the solutions, and you can kind of guess what would be a better H in some sense, right? But of course, it'll be nonlinear. Once H becomes beyond quadratic, right, then of course you have a nonlinear map. The map will be implicit, which is obviously the case, right, in general.
I see. Yeah,
it won't be
that makes sense.
Then you have to use Newton's or something, right?
Gotcha. Thank you so much.
Yeah, sounds good.
Thank you, Suku.
Okay.
Do we have any other questions from the audience? It looks like we do not. Thank you so much, Suku, for this nice presentation. It was really
Thanks
informative.
to all for listening. And sorry for the extended amount of.
Suku.
No, it was
Okay,
it was
Good
really
to see
nice.
you.
No, thank you.
Thanks. See ya. Bye.
Okay, thank you everyone, and see you next week.